Welcome to the SatPy tutorial, SciPy 2019. All of the tutorial materials are at this GitHub URL here. If you haven't followed the installation instructions already, please do so as quickly as possible. It does involve creating a Conda environment and downloading like 3 gigs of data, so it takes a little bit. I'm Dave Hoese. I'm a software developer at the University of Wisconsin-Madison at the Space Science and Engineering Center. I'm a core developer on SatPy and a member of the PyTroll open source programming group who maintains SatPy. We have 2 helpers today as far as I know. We have Jeff sitting right there. If you have any issues, raise your hand. We also have Alex, sorry. If you have any issues with installation or something not working the way you expect, raise your hand and hopefully they can come and help you. Feel free to interrupt me at any time throughout this tutorial, ask questions, ask for clarification, and hopefully everybody can have a good time. Based on the survey that about 20 of you took, we have a wide range of experiences here from all of the different technologies that I hope to use today. Nobody has used SatPy, so that's good, I guess. Yeah, so I'll try to explain what I'm doing with everything I'm using so that everybody is all the bases are covered. Yeah. Oh, also, there are instructions here if you didn't download the data and the Wi-Fi just is not working well. There are 2 USB drives. One of them is USB 3.0. If you want to grab those and continue following the installation instructions, that should save you hopefully a couple minutes. Yeah, so I think we can get started and just verify that everybody's got things going. So we're going to start by going to our terminal here. We're going to use plain Jane Jupyter Notebooks today and step through those. I will try to, this tutorial as a whole provides an overview of SatPy. I might not cover your exact use case, but hopefully I give you enough of an overview that you can see where SatPy is going and the use cases that we were trying to solve when we made it. And hopefully you can give advice on where we should go from there. Yeah, so in a terminal, we need to start Jupyter Notebook, but we need to make sure that we're in the right spot and that we're starting it with the right Python environment. Right here, I am in this long, nice path, but I'm in the root of my tutorial directory that I downloaded from GitHub, so you should have cloned the GitHub repository. You should have this. If I list what's in here, we have all of the notebooks directory. I have all the readmes and the install stuff. That's the directory you should be in. If you have some recent version of Conda, you probably have base here. We want to activate the SatPy environment that you created for this tutorial. So we'll type Conda activate SatPy to get that activated. The other thing we want to check is that all of the data directories that they exist the way they should. If I have been updating this repository over the last week or 2 with fixes based on feedback that I've gotten from some of you. So if we do an ls on the data directory, you should see an ABI L1B and a VIIRS SDR directory. The other important thing that you should see is if you do ls data /ABI L1B, you should see 2 directories in there, one that ends with CONUS and one that ends with meso. There was a bug in the original download script that only made one of those directories. If you don't have both of those directories, you should rerun the download script, which is python download data.py --data only, data dash only. That will make sure you have the zip files, it will extract them again, and then you should have all the data. So hopefully we're all generally in that spot. We can start the notebooks by typing Jupyter Notebook. This should open your browser, and we can hopefully make this bigger. So here, Jupyter Notebook, when it first opens, gives us our current, like a file browser view of what we have available. All of the lessons for this tutorial are in the notebooks directory. So if I click on that, I see a lot of IPy-NB files. We're going to start with the introduction. So click on that. That should open a new window. I would suggest keeping this Notebooks tab open so that you can go to future lessons. If you are worried about your computer's performance, you may want to shut down Notebooks after each lesson just to clear out any memory that's being used, anything that might be sitting there. Some of the processing in the later lessons can take a little bit, and it does take a little bit of memory. It will eventually finish, but if you close out old lessons, your computer may perform a little better. So, little introduction into SatPy. SatPy was created by the PyTroll open source group. It was created, PyTroll has existed since 2009-ish, 2010. I joined it in 2015. A lot of the members are based in Europe. SatPy was created as a combination of their original mpop library and my polar to grid command line tool suite. We realized we were basically doing the same thing and created SatPy as a result of that so that we could work together. So this is just a lot of scientists and programmers that all had to do the same thing and read satellite data. So let's all work together. SatPy can read data files, it can write them to different formats, it can resample data to different projections, we can make RGB composite images, we can, because of the tools that SatPy is using, we can easily access or use other visualization tools or other Python-based tools like CartoPy or GeoViews. And we'll see all of these things today, hopefully. This notebook includes some other helpful links. PyTroll does have a Slack team. If you just want to talk about working with satellite data, it doesn't have to be about SatPy, it doesn't have to be about other PyTroll libraries that we make. Just come and talk to us. So there's links to that and the various repositories. Like I mentioned earlier, hopefully everybody ran the installation instructions. That should have downloaded. That should have involved creating the content environment and downloading the data. We're going to run this simple command just to verify that things are importing and that our Jupyter Notebook is being run by our SatPy environment. So if you click on this cell, this is a code cell in Notebook, so it's got Python code in it. We can run it by hitting Shift-Enter on our keyboard, and you should get some output like this. Everything on this should say OK. That means that we have all the imports successfully in there. Maybe we'll run into some issues later, but this should be a pretty good start. Should have already downloaded the test data. Again, if you didn't, there's USB drives up here and some steps to hopefully cut through the wireless issues. So what are we working with today? We're working with Earth observing meteorological satellite instrument data. What does that mean? These satellites are Earth observing, so they're not looking at space, they're not looking at other planets. We're looking at the Earth, its atmosphere, the land, looking at the Earth. So it looks like something like that. We'll be dealing with geostationary and polar orbiting satellite instruments. These are really your two types of orbits that you end up dealing with when working with this data. A geostationary orbit, I had a coworker make some videos for me from his modeling tool. So this is an example of a geostationary orbit. You have the satellite staying over the same spot on the Earth as it orbits. You're seeing the same image every time the instrument is observing the Earth, every time it's recording data. So that's geostationary. Polar orbiting. These satellites, you can kind of see the little blip going around here. Right about here. So that is a satellite that's going from pole to pole, and throughout the day it will cover the entire Earth. It's a much lower orbit than the geostationary satellites, so it sees less of the Earth, but it's much closer, and so you typically have higher resolution data because of that, and we'll explore that more later. Today we'll be looking specifically at imager data, data from imager instruments. Essentially, this means we have 2D images, 2D arrays that we can view as images. We map some value that we have from the data to some color on the screen, whether it be grayscale or some Matplotlib color map. Our data is geolocated, so we have a lat-long pixel for every element in the array that we have. Sometimes the data is gridded, meaning it's uniformly spaced. Sometimes it is not, so we really need that lat-long coordinate for each thing, for each element, to know where it is. In general, these satellites, their detectors, their sensors are, each pixel represents some kind of circle or ellipse on the Earth. We simplify that in a lot of cases when we're looking on screens as a square. So our lat-long point that we have refers to the center of that pixel, and that pixel then has some cell height and some width, usually in meters, is how we're measuring them. These instruments have multiple bands or channels or wavelengths. You'll hear me use them interchangeably. What that means is that, we are looking at the radiance reflected or emitted from the Earth. So sun beating down on the Earth, objects will emit or reflect that, that energy, or maybe you have a fire, that fire is emitting energy. These satellites are passively receiving that radiation, that electromagnetic spectrum of radiation, and each channel on those instruments will look at a specific wavelength so that we can get different types of information about the Earth. So here in this image we have 4 different channels from the ABI instrument, and you can see that each one, although it's a different shade, there are actual differences in what's visible in the image because of what wavelength we're looking at. So some are good at looking at water vapor, some are good at looking at sea, the actual oceans, some are good at looking at snow and ice, the land, vegetation. So depending on which wavelength we're looking at, we get different information. With geostationary satellites, you also typically have sectors. So although the geostationary satellite is looking at one position of the Earth, one spot on the Earth, it has different cutouts that it can look at a different time resolution. So we might take a image of the full globe, the full Earth, from what the satellite can see every 10 minutes. We might have a smaller chunk that we look at every 5 minutes, and an even smaller chunk or 2 that we look at every 1 minute. So we get that data at different times. This allows us to get the large overview of the Earth, but when there's a storm or some interesting event, we can get very high resolution changes over time. We talked about this a little bit. Some of us in here are newer to notebooks. You don't need to be an expert in Jupyter Notebooks to do this tutorial. The basics are that there are markdown cells like this one where I have text. There are code cells like the ones we ran before with testing the installation. You can run Shift-Enter to run that cell. And if you need any other tips, you can read some of the stuff I wrote here about keyboard shortcuts, creating new cells, deleting cells. You can also hit the H key and you'll get this nice little pop-up with a lot of keyboard shortcuts. All right, we can go on to the first real data lesson. So you can close this tab if you wish. Click on Reading. You should get this reading section, reading lesson. So SatPy depends on Xray and Dask arrays. In this lesson, I'll go over some of the basic interfaces of SatPy, but we'll really be talking about what your data looks like when it comes out of SatPy or when it's loaded into SatPy, how you can access information from the Xray data array objects, and since we're using Dask arrays underneath those, what does that mean for you, the user, and how can you treat your data differently? So we'll start out in this first code cell. We'll be using the SatPy's scene object. I'll note that every notebook I start with this init notebook script. That is just a little script that I set up to set up Dask and NumPy just to make sure that everybody's machines aren't being, we're not using too many of your resources. Just kind of keeping everything in check just because there's different levels of machines in the room. Then we go to importing SatPy, importing the scene object. We use the built-in glob function here to load some file names. These are the files that you should have downloaded. And if we run this cell using Shift-Enter, we get 16 files. We can create a scene object by calling this reader, by calling the scene, passing reader. We tell it what format our data is in, so ABI L1B. We give it the file names that we have. And then we get the scene object back. Scene object acts a lot like a dictionary. So we have things like keys. So if we run this cell, we get nothing. We haven't loaded any data yet. We can ask the scene what's available. If we run this cell, we see we get 16 different channels listed. So this is the ABI instrument. We have 16 different channels. In SatPy, they're named like this. And so what we've done here by creating this scene is we've passed these file names to the reader in SatPy. It's looked through the files, figured out which file is which, what's available in the files, what's actually something that the user can load, and now we've asked it to tell us that. So we get these 16 channels. So as I mentioned in the introduction, instruments have different channels. These channels measure different wavelengths. They also typically have different resolutions to them. So for ABI, we have this long list of, well, it's not even that long, 16 channels, but some are 2 kilometer resolution, so that means every pixel refers to or represents 2 kilometers on the Earth. Some are 1,000 meters, and one of them is 250 meters. And now what we're going to do is load one of these channels. So if you're not familiar with wavelengths, I suggest just picking one for now. We'll explore them in the future, but it's up to you to just pick a channel. So pick whatever channel you want, so C07, or you'll be using that C name. So in this next cell, we have this little edit me. I'm going to use C07 here. You can use whatever you'd like to use. And then we're going to pass that string to the scene load method. We could load multiple channels. For simplicity right now, we're just going to load one. And then we're going to use typical dictionary bracket access to print out the object that is in the scene. So in Jupyter Notebooks, whatever the last line is, it will print out the representation of whatever that returns. So here we're getting a data array object. So I ran that cell. We have an Xray data array object. There are a couple important things about this. So a data array object is can be thought of like a NumPy array with extra stuff added onto it. We have dimensions added onto our NumPy array. So we have named dimensions. So we have the Y dimension. So you might think of these as rows. In SatPy, we're going to call these the Y dimension. We have 1,500 rows here. We have X, the X dimension. Those are our columns, 2,500. Here we have the data array is telling us that our data underneath is a Dask array. This is normally if you were working with NumPy arrays and you printed out a NumPy array, this is where it would print out every value. Here it's just telling us a Dask array. I'll explain why it's doing that instead of printing out values in a second. We have coordinates, so this means for every row, for every column, we have some coordinate associated with it. These are actually in meters. This has to do with projections, the projected data we're looking at, and we will talk about more about that later. And then we have attributes. So this is a lot of metadata that was either added by SatPy or came from the file directly for the particular variable we're looking at. So I loaded channel 7. Channel 7 is a brightness temperature band. That means the wavelength that it represents or that it's observing is an infrared temperature band. So we're measuring the radiance, but we can convert that into a brightness temperature. It's easier for scientists to sometimes use that. Oh, I should have also said I'm not a scientist. I'm a developer. So if you are smarter than me on this, please correct me. But I'll tell you what I know, and I think it's mostly correct. So we're looking at a brightness temperature band. Some of the lower bands, like channel 1, 2, 3, those are reflectances, so you'll have units of percent. We can see by looking at the units attribute here, I have K for Kelvin. We try to follow CF conventions typically. You have a lot of other metadata here. Things like what platform it's on, so where is it? G16, there we go, platform name GOES-16. It's also referred to as GOES East, so that comes from the metadata inside the file. So we just have a lot of metadata. Oh, start time and end time, those are also important. So that's when the instrument started observing the data we're looking at and how long it took. That's our end time. As far as geolocation, we have the coordinates for the rows and columns. This is gridded data, so this means in X and Y projected space, every column's at the same coordinate, every row's at the same coordinate. We'll talk more about that when we get to projections and resampling, but the way SatPy encodes all of this stuff is through this area attribute, this area piece of metadata. It's an actual object, and we'll learn to use that more and what that represents and what that means later on. So we have some metadata. We can, with a data array, we can access that metadata through the .adders property. So we can do scene bracket my channel. So that gets us that data array. On the data array .adders, and then we can say, we can treat .adders like a dictionary and say, give me the start time. We get that date time object for our data. We have also access to the dimensions, so we can get a list of the dimensions I mentioned before, Y for rows, X for columns. We can check how big those are by using the sizes dictionary, get the number of those. Data arrays also have properties that you might see on a NumPy array, so we still have access to shape. We also have access to the ndim property, so we have a two-dimensional array here. And if you're looking at a different resolution band, you might see different numbers for the rows and columns. Okay, and although it's not typically needed, we do have access to the Dask array underneath the data array. So the data array is the large overall container that holds on to our dimension names, our coordinates, our metadata, and it holds on to some pointer to our data array. So this could be a NumPy array, but in SatPy we're using Dask arrays. And so when we do this, you might get something like this, depending on what version of some of the libraries you have. Some things have changed recently. So you might see this where it prints out a representation, a string representation of the object. You might also see a little graphic showing you like a tan chunk that has boxes in it. That's trying to show you what this Dask array looks like. It gives you some other stats about how much memory it's using. So that's available in, I think, newer versions of Dask. Delayed calculations. Dask arrays, we use Dask arrays in SatPy because we're typically dealing with more data than, throughout our operations, we end up using more data and more memory than we can actually hold on our machine. We don't want to swap data onto the hard disk. That just makes things slow. We would like to just compute things as best we can with the memory available. So that's why we're using Dask arrays. The other thing about Dask arrays is that it automatically runs things in parallel. So it'll use multiple threads, do things in parallel. We can do things faster. The way it achieves this, the way it looks to us as the users, is that everything is delayed. We don't see the actual results. We don't have to wait for the results as we're preparing these calculations. So we can see this in this code cell. We're going to create a new Python variable. We're going to access that data array. We're going to add 2.5. So even though I have a, 2500 by 1500 array that finished instantly, because Dask isn't actually running through each of those pixels and adding that 2.5. And this is an arbitrary example. Adding 2.5 isn't some scientific purpose. Yeah, Dask is building a graph of these calculations that we're building up over time, and it's not actually going to perform those until we tell it to perform those operations. We can print out what my new var is. We see we get a data array. It still has those dimensions that we had. It still has a Dask array underneath, and it still has some coordinates, same coordinates as before. We lost all of our attributes. This is the way Xray is working by default. It's assuming that we did some calculations, so the metadata might not apply. So just to be safe, it's going to remove the attributes. If we wanted the attributes to still apply to this new data array, we'd have to manually set those again. This whole delayed operation concept can get a little confusing when you're used to working with NumPy arrays because you might want a result right away. So let's say we want to know the maximum value in our channel that we loaded. We run .max and we see some text, but it's not a number. This is a new data array that Max produced. You can see that by the dimensions, which would normally be right here, we have no dimensions, we have no shape. This is a scalar array, so this is one single value, which we expect. We're getting the single maximum value for this whole data array. But it didn't actually compute anything yet. The way we can do that is ask Xray to ask Dask to compute this thing. We do that by running the compute method. So we run that and we get a data array that actually has a NumPy array underneath. Because it's fully computed, it's not a Dask array that's delaying these operations. We have a NumPy array with a real value in it. So 411 for the data that I loaded. We can also compute from our new var that we made where we added 2.5. We can see it's 2.5 greater. So even though we got a new data array, nothing was done in place. We computed these things, we got the results we wanted, but we had to ask to compute them. Another common operation you'll see if you're Googling things about Xray and Dask is using .values. If we use .values, we don't get a data array back, we get the NumPy array underneath. Because we're using Dask arrays, this produces the computed NumPy array underneath implicitly. So even though we didn't run .compute, .values is computing that data array still, or the Dask array still. These operations are a lot like using NumPy arrays, except for the compute part of it. But we can use data arrays a lot like NumPy arrays. So if we start running some Matplotlib code and we want to make a plot, we can give it a data array and it will create our plot for us. So here we imported Matplotlib's PyPlot as PLT. I created a figure, so give me some image where I can put data on it. I'm running imShow or image show, and I'm giving it that scene data array object. And then I asked for a color bar. So this is what I got back. Got no labels, but I have a color bar, and this is what our data looks like. So you can kind of pick out that this is looking at the US. This upper left corner here, this is actually space, where the satellite is looking just off the edge of the Earth on this CONUS view. CONUS, continental United States, that's what this sector is for ABI. So this was passing data arrays to Matplotlib. Xray also comes with its own utilities for plotting. We can access these. We'll create a new figure first, but we can access these through this plot attribute. And then there are your typical .plot, .imShow functions. We're going to use imShow. I'm going to specify the color map explicitly. And I run this. Oops. And so now I get pretty much the same image that I had before with some key differences. I'll stretch this out. It didn't. There we go. So we see that our color bar now has a label. This label is coming from the long name attribute from the data array. So Xray is making some educated guesses. You have these attributes. These are typically used as this type of label in our plots. So it's going to use the long name. It took the units and put that in brackets there. It labeled our dimensions for us. So our X dimension, our Y dimension, our axes, it labeled those for us. In some cases, it will also add a title for us depending on what data we're looking at and what the attributes are set up as. Yeah, so it's a nice little utility. Because it's using Matplotlib underneath, we still have access. We could add a title if we wanted, so we could do something like plt.title here, and I could say, I don't know, C07, or maybe my channel C07. I rerun that. Now I have my title, so I can do all my normal Matplotlib functionality by doing that. Another thing you can do here is, if you're familiar with using the vmin or vmax keyword arguments in Matplotlib, you might want to use those to limit that color bar range. So I see with my data, I'm going from about 240 to 400. Maybe that's not what I actually want to look at. Maybe I want to look from 300 to vmax 380. So we can specify these keyword arguments here. And now I get a darker image. Okay, maybe that was a bad choice, Dave, but get a different image. I can specify vmin, vmax. This is important later on when we might be looking at differences or things that have outliers that we don't want them to make our color bar not look so great. So vmin, vmax, cmap, if we wanted to change this, we could also make this magma is another popular color map. Maybe I'll remove vmin, vmax. So cmap equals some color map name, so these are all Matplotlib color map names. We get a different image. Oh, I should also point out, since we're using Matplotlib, when I created my figure before, I added this Matplotlib notebook magic command. This is telling Matplotlib that we want to use its interactive widgets so that we can actually interactively move around our image. So you can use this, this empty square here is your zoom rectangle. So we can click on that, and then if we drag a little square, it will zoom into that square of data. If we want to go back, well actually if we want to pan and zoom, we can click on these four arrows here and move around, so we can move around on our data. If we want to go back to our full view, we can click the home. If you wanted to save this image as a PNG plot, you could either run the normal Matplotlib commands to run and save that, or you could click the download button. So that's how we're going to be using Matplotlib today. Just to explore our data and look at it. We'll do other things to look at our data, but this is the easiest way when looking in notebooks, looking at an interactive environment. I listed here some other color maps that you could use. Some of these are more useful than others, and some I just thought they made weird images, kind of going on that whole jet route of color maps, just having fun with it. So you could try those out too. Does anybody have any questions so far?
So how smart is DAS? Like, when you did that plot over and over again, is it actually rereading everything, or does it know it already did that once and it's moving on?
So the question was, is Dask smart enough to realize when we were making the plots, was Dask being recomputed every time? Right. And the answer is yes. I'll go over some ways to help with that, get around that, but yes, luckily right now we were only loading data from disk with like a few scaling calculations, and boom, it was on the plot. Oh, I should have mentioned this before. On the terminal, if you created your Conda environment, I'd say more than a week ago, and you haven't updated Xray, you should do that either now or on a break and restart your notebooks. I believe it's 0.12.2. This includes a bug fix by me that I discovered while I was making these notebooks, that Xray's utilities are actually computing the Dask arrays twice every time you make a plot. So it's not a huge deal right now because we're just plotting data from the file, but when we get into making RGBs and things that have more calculations, you end up waiting a minute for things that shouldn't take that long. So if you need help with that, maybe raise your hand and talk to the helpers. You can check it by running conda list xarray in your terminal, but we can talk about it when we get to the breaks and stuff. Hopefully it won't affect anybody. But if you created, I think that release, I forget what the PyPI page said, but I think it's been out for like a week. So if you created it within the last week, you should be fine. Yeah, So, yes, question.
Also a question about the interactive tools for the plotting. Can you also save them, such as if you zoom at some place, you can use this zoom area for all the next plots? Can you script that?
I believe that would be Matplotlib functionality. You're saying. So the question was, if you zoom in on a part of the plot, can you reuse that for later plots?
Indeed, yeah.
Not interactively through Matplotlib, as far as I know, and what I'm doing with it here. We're going to talk about slicing in a bit, and we'll talk about cutting out areas of the data programmatically using SatPy based on the geolocation. We'll talk about that later. But as far as selecting an area in Matplotlib and then using that later, I know that a lot of people are working on that, and I'm sure it exists in a lot of different libraries that are already out there. I will not be using that today, though. Yeah.
So when you're saving that certain selection of the PNG, does that also save all of the coordinates within that data set that you're looking at, or in the current selection that you have, or is it saving it from the whole data set that's already registering in the image?
So if I zoomed in, you're saying if I went like this, and then I save this, is it saving every data point?
Yeah, or is it just that location that you're shooting?
It's gonna save, so the question is, if I zoom in like this and I save this image, is it saving every data point of the whole image? What is it doing? So this is all through Matplotlib, and this is saving the actual PNG colors of the plot. It's not looking at every data pixel. It's not even looking at the real data that made this plot, because there's a very, if I go, so I think my data was 1500 by 2500. That's not how many pixels are in this image. And so Matplotlib is interpolating or whatever it wants to do to make the image fit in this plot. And so yeah, so it's not saving every data point. It's saving whatever it has to make this image just red, green, blue, RGB, PNG pixels. Okay. Move on to slicing. So I talked about how data arrays can be used a lot like NumPy arrays. Part of using NumPy arrays are getting the exact row and column that you want. We can do that with data arrays also. Here we're going to call the scene.load method again. Even though we created the scene and we loaded before, we can load more data later if we want to. So here we're going to load channel 2. If you loaded channel 2 already, it's fine to rerun this. That's okay. It should realize that it's already loaded. And then we can use slicing. We can also use a property of slicing called striding. So here we're using, this is our Y dimension, our rows. We can say we have this start index that we want. We have this end index, and we want every 4 pixels. Same thing for the columns. Start at this index, go to this index, get every 4 pixels. If we run this, the data array that was sliced will give us a new data array back. It realizes that we're looking at a smaller chunk of our big data array. So it keeps all the dimensions, it keeps the coordinates, but it also strides those coordinates for us, slices those coordinates, and we keep all of our metadata. You can see that through the striding, I have 250 pixels by 250 pixels. And we can use this just like any other data array and plot a Matplotlib figure. So we run this, we use those utilities that we learned how to use, and we get every 4 pixels. You might be able to tell, well, obviously we're looking at a smaller chunk of the data, but it's also a lower resolution because we're only looking at every 4 pixels of the original data. So what I would like to do now is take 5 to 10 minutes and learn what we learned about with Matplotlib, load different bands, see if you can see the differences in the different channels. So remember that we had C01 up to C16. So you can use the scene load method and load that. Feel free to play around with the vmin, vmax, look at color maps. So take 5 to 10 minutes and explore the different bands, see what you see. We'll use these bands later on, combining them, but if you find one that you think looks better than the others, maybe use that in the future lessons as we go along. So take 5 to 10 minutes, and feel free to raise your hand, ask questions of me or the helpers. And yeah, so we'll come back at 50. 8:50 we'll start again. Does somebody have this other jump drive? Yeah, it's over there. I bought it at Target last night. I want it back. Oh, and also explore the data, use the interactive Matplotlib tools. You may have guessed by the names of the files that you downloaded for this data that there's a particular event in these files, so you might be able to find that by zooming in. Yeah.
So I noticed that all the data we're using is pretty low resolution in terms of the pixel, pixel size to land size. How much has is SatPy kind of designed around like the GOES satellite and these kinds of broad looking satellites, or have you started any kind of work into using higher resolution satellites within the library? So, something maybe down to a meter or a third of a meter.
So the question is SatPy, does SatPy do anything with higher resolution satellites or higher resolution data? Do you have an instrument in mind that has that resolution?
The digital globe satellites would all have that resolution.
Okay, and do those measure, are those remote sensing satellites that measure wavelengths?
Yes.
Okay. No, I have not done that. We'll see later in this lesson that SatPy has a lot of readers. We have contributors that work with EUMETSAT and different European organizations. I do a lot of work with NOAA and NASA, and so I use a lot of the data that they're providing. Another thing I could have pointed out earlier is we'll be looking at what's called level 1 data, so that's like the radiance data. There's level 0, that's what we get directly from the instrument. You can also have level 2 data where people have taken that level 1 and said, oh, I see this wavelength sees this wavelength sees this, I know that there's clouds, or I know there's this type of cloud. So we support reading all of that type of data. There's also different types of instruments, but as far as like remote sensing imager instruments, as far as I know, GOES is the highest resolution NOAA one for geostationary. But yeah, I've never had to use anything higher than that, or been told of anything higher than that. So maybe we can talk later. All right, why don't we bring it back? So a couple questions came up during this. One thing some people had issues with is you do have to explicitly load a new channel. Even though it says it's available through that available data set names, you do have to load it to access it later, to actually use the data. Another thing that came up is questions about what readers does SatPy have. We'll see a function in a little bit that actually lists what readers you have available and what ones you have all of the dependencies installed for. They're also listed on the SatPy documentation, satpy.readthedocs.io. There's a nice big long table here of what's supported. SatPy and the PyTroll organization is not run by a company or funded directly at all. It's all volunteers working at different agencies across the world, and so a lot of the readers are added by necessity. So as far as I know, we don't have anything for Landsat, but that's just because nobody's been needing it yet. There's documentation on how to create your own reader. But yeah, me personally, I get paid to do a lot of stuff with NOAA satellites and NASA satellites, or the products that they produce. And so that's where the readers I've contributed come from. But we have developers all over Europe. They work with Russian satellites and EUMETSAT, European satellites, China and Japan, India, Australia. So whatever these developers, these contributors ended up needing, they probably contributed those readers. Yeah, so that's where those came from. Another question that came up is, why can't you do something like, I have scene 02, and I want to change a specific value. I want to say, okay, the value at 0, 0, I want it to equal 5 now. Well, I can't do that. This variable's data is stored in a Dask array, which does not support item assignment. To assign to this variable, you must first load it into memory explicitly using the load method or access it with dot values. So based on how, or because of how Dask works, we are creating this these series of tasks that we are doing to get our final Dask array that we're using. We can't change a task once it exists on that series of tasks. We have to create a new task that affects the result of the array. So one way to do that, you may be familiar with the numpy.where function. There is a Dask where function. So I'm just going to show this quick. You don't have to follow along with this part because this is just proof of concept, I guess. So if I do da.where, and hopefully this works because I've never tested this, greater than or equal to 300, and I say set it to 50. And of course that doesn't work. Oh, because I'm using, okay. 100. Yeah, so I get a new Dask array. This has a new set of tasks that are built from that first Dask array I had, and I get something else. Most NumPy functions now, based on the work that NumPy and Dask and Xray have done, you can pass Dask arrays or Xray data array objects to NumPy functions, and they will return a Dask array or a data array, whatever you originally gave it. It'll give you that same type back. Where is one of those functions that, as far as I know, doesn't do that. If I did import numpy as np, and I did numpy.where, I'm not sure what this will return. Yeah, so that actually computed the data and returned a numpy array. So there's a couple functions like that that have to be computed based on how NumPy is structuring things. I'm sure those will change over time as far as they can. If you're curious about it, I'm sure there are plenty of NumPy and Dask developers here at this conference this week that you could talk to about it. So let's move on a little further. Any other questions regarding that? No. Okay. One thing I didn't mention is with Xray, we can slice things based on those coordinates that we have. We can use this .cell select method on the data array object. We can specify the dimension that we want to slice, and we can slice based on some of those values. And so here for mine, for the channel I loaded, and this should work for yours also, I can slice based on some metered values. So I mentioned those X and Y coordinates are in meters. I can slice based on those using this fancy slice object. If you're not familiar, the slice object is the actual object that gets used when you use that colon syntax in your brackets. So we can create these and slice our data array based on the coordinates rather than the index. This is very useful if you're very familiar with your geographic coordinates in a certain projection. So you're actually slicing into your array with the data's coordinates, not the actual data, not some array location. Next up, accessing data in different ways. So I mentioned that every channel represents a wavelength. If you were using higher level products like cloud type, what type of cloud is this? That doesn't have a wavelength associated with it, but for the data we're working with right now, each channel has a wavelength associated to it. We can access that by doing, by getting this wavelength attribute, so .adders wavelength, and this will print out a 3-element tuple where the middle number is the nominal wavelength, so this is what the instrument was designed to observe. It's meant to see is a bad word. I'm not a scientist, so I can say that. So 3.9 is what this channel is meant to be recording, observing, but based on the design and the engineering of the instrument, it sees a little wider outside of that exact wavelength. So this is what this is trying to tell you, is that anything between 3.8 and 4.0 could be observed by this channel. If we use this, we can use this wavelength number instead of the channel name in our scene. This is very helpful for scientists who get used to using the wavelengths instead of the channels, because if I use a different satellite. Even if it's the same like family of instruments, so ABI we're using right now, there's a Himawari AHI instrument, which is the same type of design, but it has different channel numbers with slightly different wavelengths. But we know we want the 3.9, so I can use the in syntax to say, oh, is there a 3.9 wavelength channel in this scene? And I don't have to use the exact wavelength. I can do something like 3.85. This is useful because anything within that range I can use. This is useful because of the engineering, like I mentioned, or just by the specification for the instrument. It might not be the exact wavelength, but it's pretty close, so I can still do the same type of science that I want to do with something close enough. We can use this with the same bracket syntax that we've been using before, but instead of using the string channel name, I can use the wavelength. We could use this in the load method as well. Yeah, just another way to access things. And we'll do a quick little mention on geolocation. A lot of people are used to using longitude and latitude arrays to locate their data or to have points for everything. We can get access to those arrays with the area attribute. It has a get_lon_lats method to it. So if we do this, it takes a little bit and we get this big long NumPy array of all the longitude and latitude coordinates. We could have it return a Dask array if we wanted to say chunks equals 2048. This is just a way to basically tell SatPy and the libraries underneath that it should break up these arrays into Dask arrays. And so we run this and then we get a Dask array back right away. If that's what you want to use, that's how you can do that. It's not necessary to usually use raw longitude-latitude arrays with SatPy, but I wanted to mention it here. It is important to know what an area object is, and like I said, we'll do this more later, but I want to point it out now just so things make sense. So the area for our ABI data is an area definition object that comes from the PyResample library. That's used to define gridded, projected data. And if we print it out, we get information about projection and the size and where our data is in this projection space. And so that's how SatPy is encoding all of this information about geolocation. And we'll use that later on. Lastly, if you want to see what readers you have available to you based on what your environment has installed, you can run this available readers function. So if I run this, I get a ton of warnings because it's trying to import things that I don't have the functions for or the dependencies for. But I get this nice long list of reader names that I can use to read data files. And like I said, this is also on the SatPy documentation website. So there's a big long table. I don't think these are alphabetical. They mostly are. Yeah, so there's a list there with a small description of what they're doing. And yeah, any questions on reading or basic Dask data array stuff before we move on to the next lesson? No. All right, I'm going to close this tab. I'm going to shut it down just to show how to do that. So I'm going to check the box on this notebooks page and click shutdown. Actually, I'm going to do that for introduction too. So that killed the Python environment that was running that notebook. I don't need it anymore, so it's not necessary to have it. So I'm going to open writing, O3 writing. So a very common thing that we work with in SatPy is needing to give data that we either created or loaded with SatPy to somebody else who's not familiar with Python, not familiar with SatPy, or they're required to use some visualization client that doesn't support the raw data files that we have. Here in the lessons that we're doing today, we're lucky that the data files we're using are NetCDF and HDF5, which are fairly popular, fairly easy to read. There are a lot of data file formats out there that are just random binary custom things that are very difficult to read. That's one of the benefits of having readers that everybody can use. So there are some clients, like the National Weather Service for the US has to use AWIPS to view their data. AWIPS only supports certain file formats. So we need to have a way to convert to something that can read. Another popular one is a web mapping service or a WMS server. You typically use GeoTips with those. So we might want to make some GeoTips. SatPy comes with a couple writers. We can use available writers, the available writers function, just like we did available readers. We can run this. Get a warning probably if you don't have dependencies for some of the writers, but here are some of the ones that exist. Some of them are like proprietary formats for things that contributors needed. They come with SatPy because they're not overly complicated and just have a few dependencies. But we have the ones we'll be talking about today are the GeoTIFF writer, simple image like PNGs and JPEGs, and the CF writer for trying to write CF standard netcdf files. So we'll go on to the next cell. We're gonna talk about making GeoTIFFs. So we're gonna have you pick a channel again. I'm gonna do channel 7 again. Change that edit me to say whatever channel name you want. We're gonna load the same files we were looking at before. We're gonna create a scene. We're gonna do scene.load to load that channel. And in the least exciting way possible, we're gonna run one function, one method, and we're gonna get a GeoTIFF. So what this did, this saved datasets method on the scene, by default will take every channel you've loaded and try to write it out to a fairly default generic GeoTIFF file. It uses a lot of the same defaults that Goodle or GDAL has. We can use, in notebooks, you can use an exclamation mark to run shell commands, so commands that you would normally run in your terminal. So hopefully this works for everybody. I didn't have a lot of Windows testers for this tutorial, so hopefully this works on all Windows machines. But I can run pwd to list what my current directory is. So it's telling me I'm in notebooks, my notebooks directory of this tutorial. I run ls to list the directory. And I now see that I have a C07 with a date.tiff. I can use the Goodle info command to list out information. This comes from the C Goodle library, GDAL, however you want to pronounce it. I'm using a question mark here to just as a wildcard. So whatever channel you chose, this command should work for you. From Goodle's output, we see some size information about this GeoTIFF. We see some projection, geolocation information about it. We have metadata in here that SatPy added, like the start time, the date time of the image. We can see that it's using deflate compression by default. And then at the bottom here, we can see there are 2 bands in this file. So our data is a single 2D array. By default, what SatPy is storing is called an LA image, or luminance plus alpha. This means that the value or the level of gray is in the first band, so that's where our real data is. The second band is an alpha band that determines what's transparent in our image. So if it's 0, then it's all transparent. If it's 255, then it's all opaque. I think that's right. We can look at this image if you go to your operating system's file browser and navigate to where this GeoTIFF is. So if you go to your tutorial, can I make this bigger? Ooh, that's kind of ugly. I can navigate to notebooks, and on Mac, this should open in preview. If I double click on this GeoTIFF, I get an image like this. If you do this on Windows, I think there's your default photo viewer. Linux should use ImageMagick if you have it installed. But you can open this GeoTIFF. If you had some visualization client like ArcGIS, QGIS, a WMS server, if you really wanted to start one up and upload it, this GeoTIFF should work fine for that. You may notice that this looks a little different than it did in Matplotlib. That's because there's an extra step going on here in SatPy where it has to convert our float observed data values to something the image can understand, something that fits inside the image, which is an 8-bit unsigned integer. So there's just some extra enhancement steps is what we call them. This will come into play even more in later lessons, but just know that there's that extra step there. Yeah.
Why is it that you're writing in 8-bit if you're using raster IO for the write process, right?
Mm-hmm.
why are you writing in 8-bit? Because you have the capability of writing in the 32-bit float or 16-bit integer.
So the question was, why are we writing 8-bit integers instead of floats? I guess my question to you is, what applications do you use that can read float GeoTips?
You just mentioned them, ArcGIS, QGIS,
Okay.
non-just visualization.
For viewing images, my experience, image viewers can't understand the float data, and also if you are, like Preview and Mac doesn't understand float TIFFs. If you, the other thing is, are you saving a float and scaling it to 0 to 1, or are you saving it and storing the raw data? So are you normalizing the data before you're writing it out to the GeoTIFF? There's just different use cases, and what we'll do next is actually write out a float GeoTIFF. So that is what that image looked like. I should have pointed out there's like the space pixels, those aren't considered valid data with ABI, so those were transparent. Another type of GeoTIFF that is very common is called a cloud optimized GeoTIFF, also called a tiled GeoTIFF. This is just a different way of writing the data to disk. It compresses better, and it's much easier. It works very well for WMS servers, those web mapping services. It's also supposed to work very well if you were storing these GeoTIFFs on cloud storage, because you can read individual tiles instead of the default, which is to write row by row to disk. If you're curious, there's links in this notebook to COG, so that explains what cloud optimized GeoTIFFs are. If you're familiar with the Pangeo project, they prefer that GeoTIFFs be written as cloud optimized GeoTIFFs so that they are more friendly to cloud computing resources. So we can run this, or we can create these by specifying some extra keyword arguments to our save datasets method. Any that are available in raster.io or Google, which is used by raster.io, can be passed here. So we can say tiled equals true, and we'll run this. I added in this cell the Dask diagnostics progress bar. This will detect inside this with statement. This will detect inside the with block. This will detect anytime a Dask array is computed and show us a progress bar for that computation. So we see it took about 0.3 seconds on my laptop, and it wrote that GeoTIFF. If we do an ls again, oops, we see we still have the C07. SatPy by default doesn't care about overwriting files. It assumes you, the user, knew that you were going to overwrite that. We can run Google info again, and the main difference here is that this block parameter says that it wrote a square of data instead of a line of data. So that's that tiled operation. Otherwise, everything else is the same. As was mentioned with the question, sometimes you want to write float data. I mentioned there was that enhancement step. If you want to write the raw data values, so those, I talked about brightness temperatures, there's also those reflectance values. Sometimes you don't want to scale them to some other smaller data type, like an 8-bit integer. You want to save the raw float values. We can do that by passing some additional keyword arguments to save data sets. We can also tell it to save to some other directory. So I'm going to do that here by specifying base dir and say put everything in a float images directory. I can customize the file name and specify that I want it to be named whatever the name of the channel is with a .float.tiff. That's what I want to name this. I can specify what data type the output should be, so a NumPy 32-bit float. And I can turn off the enhancement, that conversion from observed data values to image values by saying enhance equals false. And if I run this, I'll get a progress bar. And we can ls. I see here that I have a float images directory now. So that was created automatically if it didn't exist. If I ls float images, I see I have a single GeoTIFF there. A nice key point about this, I guess, is I can specify anything in this format string, anything that's in the .adders dictionary. This can be very helpful if you have some long custom name that you need, or you need things in a different order. From earlier steps, we had C07 with the start time. Maybe you want the end time. Maybe you want the standard name in the file name. Maybe you want that platform name. And you can access those by using a standard Python format string like this. So curly brace, whatever the name of the attribute is, and end curly brace. So Google info on this. We see here that instead of 2 bands at the bottom, we have 1 band. It says it's a float 32 data array image, and that are no data values. So where there is bad missing data, it'll be nan in this output image. Yeah, so that's how you make a float GeoTIFF, if you need to do that with whatever applications you use. So take a couple minutes real quick, just so that this lesson has some amount of customization, and see if you can change the file name and add things like start time or standard name, and just do that real quick, just for like a minute, and I'll show you something cool if nobody's familiar with it after that. So just take a minute or two to play with the file name, and if you have any questions, feel free to ask now, and yeah, we'll get back in a minute or two. Any other questions before I do a quick example? Okay, so one thing I wanted to point out before we go too far is, let's do this. I'm going to select this cell. I'm going to hit B, and this gives me a new cell underneath. I'm going to do scene.saveDatasets. You don't have to type this if you don't want to. This is just me playing with stuff. So like I said, we can use anything that is in the attributes in our file name here. So I did .tiff, or sorry, just start name like this, and I save this, and I do an ls. I get kind of this ugly file name, at least I think it's ugly, where it has the name, and it by default it formatted that datetime object like this. If you aren't familiar with Python format strings, you can customize how datetime objects are formatted right in the string. So if you do colon after the name of the attribute, I can do things like you would normally pass to string format time, or string f, strf time. So %y, %m, %d, %h, %m. So maybe I didn't need the seconds in my file name. So now I see that I have this this hour and minute file name, and I didn't have to do anything fancy with the date time. I added some stuff to the format string. So nice little trick if you didn't know it existed. How you do? Another format that's very common is PNGs. If you don't want to make plots, but you want a real one-to-one scale of this data pixel is a pixel in my output image, I don't want any interpolation, I want the full image. You can use save datasets and use this simple image writer. By default, this will make a PNG image. You may notice from the progress bar that this took longer than the last one. That's because by using raster.io, we're able to use Dask more effectively to write to the file in parallel. As far as I know, it's not possible to do that with PNG, at least with the way that the pill library implements it. So it's a little slower. Our images are small enough that this isn't a huge deal. If I list this, I have this PNG image. I could go back to my file browser, PNG, same kind of output as I had with the GeoTIFF as far as the way I'm looking at it. If we do save datasets, will also guess what writer it should use based on the file name. So if we do file name equals, I say something like test.png, it will also make that PNG based on the file name. So I could do .tiff, it would guess that it would be GeoTIFF, but yeah, so if you did .jpeg there, that should work. There are some gotchas with that, just based on what kind of data you can write to JPEG. Yeah, so it will guess at what writer you're trying to use. Lastly, for writers today, there are other writers, but most of them are specific to specific visualization clients. So we'll talk about netcdf, which everybody should hopefully be kind of familiar with. You store your data in a netcdf file. It's supposed to be self-describing. There are CF conventions. So can anybody I think it's climate forecast. Is that what that stands for? Climate forecast standard. Yeah, climate and forecast. So these are standard attributes that you should have with your netcdf file to make them more self-describing, to be more useful to more applications. So we can create the same scene object that we created before, and we're going to load 3 channels at once, so 7, 8, and 9. We're going to use that progress bar. We're going to call save datasets again. Here we're going to tell it we want to make a netcdf file, and we're telling it what engine to use. Engine isn't technically needed. This was a bug in, there was a bug in past versions of SatPy where the engine wasn't set properly depending on what you had installed. There are different netcdf libraries that you could use. So here I'm explicitly saying engine netcdf4. If you have an older version of these tutorials, it might not have that. You may want to specify it here. But I run this, and now we get multiple progress bars. That's because it's not only saving the channel data for the 3 channels, it's also saving the longitude latitude data, so it has to compute those values. I think, yeah, so there's 5, so that should be good. There's a warning here about there's not extra time information. I could argue that that warning doesn't need to be there. If we list our directory, we see that we get the file that we specified in the file name keyword argument. We can use the nc dump command and -h to say give us the header, give us the information about this netcdf file. We get this nice long output of what was written to our netcdf file. So like I said, this is the CF writer in SatPy, and it's trying to generate a CF standard netcdf file. And we're making improvements every release. But you have the X and Y coordinates, so these are those 1D arrays that are the metered coordinates for that data. Longitude and latitude 2D arrays, there's options to turn the generation of these off. We have the data arrays with all of the attributes in there that could be converted to netcdf, written to them. By default, this is writing float data. Xray has its own utilities for writing netcdf files. It can't parse everything that SatPy uses, and it also does some other things that are slightly different to what SatPy is doing and how it's writing its netcdf file. And there's global attributes about what CF standard we're trying to go with and what software created this netcdf file. So that was the shorter lesson, but I thought it was important that if you need to use GeoTips or netcdf files, there is this functionality in here. It can be very useful if you're working with this data. I would say reading the data from the files is the hardest part about using satellite data, satellite instrument data. But usually you have to give it to your colleagues if they need to do something outside of Python or there's a visualization tool that you want to use. So being able to save these formats should hopefully be easy, and that's what we tried to do here in SatPy. So any questions before we move on to something else?
Are you familiar with NCO at all?
Could you tell me what that's?
NetCDF files, the command line.
Say that again?
It manipulates NetCDF files with the command line.
Okay. The question is, do I know what NCO is?
It's not a huge deal. Okay, so the guy who writes it, he absolutely hates having NAND as fill values. Now, as an engineer, I love having NAND as a fill value because that's what it's there for, but he hates it. So I was wondering, like, is there a way to write these out and have something, like, be able to specify what the fill value is, and so it's not NAND? Xray, writing it out with a fill value other than NAND is actually quite difficult.
With NCO, you said?
Xray, it is
Oh.
hard to write out a netcdf file that has something other than NAND as a fill value.
Pull requests are welcome.
Okay, no, that's, you see that, yes, right.
Yeah, so the
I mean, like, what do you do for, like, int values? Do you just pick something?
int values, well, that's an interesting topic. So the original question was, is there a way to set a fill value other than NaN? Because some people prefer not to have NaN as a fill value in netcdf files. I understand it can be hard to deal with sometimes. I also agree with you that NaN it's a good value to use for that. I wish integers had a NaN value. I wish there were maybe multiple NaN values that were easily to access with NumPy. There are not. So the answer is no, there's not right now.
Okay.
There's another question after that. But anyway,
For ints.
oh, what do you do for ints? So SatPy, I would say it's a relatively recent standard practice that we're trying to stick with is for integer fields, we try to use the underscore fill value that you might see with netcdf files. We try to keep that along with our data arrays that we use in SatPy. One problem that you might run into if you're used to working with integers is that in Xray, doing certain operations, it will change the data type of your data. So if you have integers and you say, I want to mask out everything, I want to replace every value, so using that where function, I want to replace every value that's greater than this with 0. It might, I think there's some gotchas, I can't be sure, but it might change your data type to something like float. That's because underneath, Xray it defaults to using nan as its fill value. So if you have integers, nan is not an integer. SatPy tries to preserve data types as best it can. It does that by detecting that there's a fill value and that we have an integer data array and keeping track of those things because it's very important in working with like level 2 products where you have things like you have category products like cloud type where a cloud being type 0 is not the same. A cloud being type 0 and a cloud being type 2, the clouds in between them are not necessarily type 1. So doing any type of interpolation or averaging, you need to be really careful in keeping things as integers. So it's a heavy loaded concept.
You guys looked into using something like a binary mask or something like that?
Have we thought about using a binary mask? SatPy has gone through many revisions. We used to use masked arrays for everything before we used Dask arrays. We switched to using Dask arrays, which meant it was easiest to use nan as a fill value for everything. And that just reduces the amount of memory you're using because you don't have the data and a mask. That was a major plus. Now Dask arrays support masked arrays much better, as far as I understand based on what I've read. So maybe that's something we could do in the future, but yeah. Right now it's not heavily needed by us and we're doing okay. So yeah. All right, any other questions? Okay.
Is there a way to divide when you're doing the write process, if you hit a wall that says that the maximum file size can be this much, will it automatically split it up into grids and write it into smaller, like let's say you're going to write a 300 gigabyte zip file. Is it going to split it up into smaller chunks? Or is there a way to provide that?
So the question is, if I'm saving a ton of data to something like a GeoTiff, will SatPy automatically split that into multiple files? The
Or
answer,
even to specify, if we can specify the control, like.
there is not. There are writers that by design are meant to do that. Like the SCMI writer is a netcdf writer for AWIPS, for the National Weather Service that I wrote. That is based on the idea of writing tiled netcdf files, so a netcdf file for each tile, and so it by default does that. There's nothing like that for GeoTiff. We're pretty plainly using raster.io, just selectively writing tiles one at a time. Okay. All right, I think that's it for writing. Let's go on to the super fun concept of resampling. I say it like that. I'm going to shut down the writing notebook, by the way. So resampling tab. So I said that like that because resampling, if you're not used to this, is one of the most complex topics to explain and really understand. Normally, hopefully, you don't have to fully understand them to do your own work, but because of the concepts involved, it's good to have a small little handle on them because they do provide you with some nice functionality or give you some availability to do other things that you might not be able to do. So let's start out with a quote from the Map Projections book by Battersby. So map projection is the process of transforming angular, spherical or elliptical coordinates into planar coordinates. All map projections introduce distortion to areas or angles or distances in the resulting planar coordinates. Understanding what, where, and how much distortion is introduced is an important consideration for spatial computations and visual interpretation of spatial patterns, as well as for general aesthetics of any map. So what that means is that typically we model the Earth as a sphere or a spheroid, so a sphere that's smushed a little bit. That's not a perfect representation of the Earth. There are certain distortions. We are working on computer screens. That's a 2D surface. It would be nice if our data was on a 2D surface so that we can do more calculations, or so that we can see things better. But you can imagine if you take it's globe versus map. If you take the globe and you try to smush it on a flat surface, things get distorted. They don't look great. So there are different ways you can make a flat surface from the round-ish Earth. Here are some examples in this image. So we could take a flat surface, place it on top of the globe, and project the Earth onto that surface. And so you might get something that looks like this bottom image in the first column. So just what you're seeing from the Earth from that flat surface. We could use different shapes. So in the middle column here, we're using a cone. If you project the Earth onto that cone, you cut that cone and you flatten it, you might get something that like this middle column on the bottom there. So you can see it looks like a cone that was cut. You might use a cylinder, so you get something like that's in the right. One thing you might notice in these images is that, especially like in the cone, there's this blue line here in the middle of the cone. That's where the cone is intersecting the Earth. This is kind of where your reference longitude, where the distortion is the least, where you're referencing all your coordinates from. Depending on how you change the shape of the cone, how far you put it into the Earth, how you expand it, you can get different coordinates, different results, different distortions. And so some people have their favorite projections for where their data is that they're looking at, and it is its own science of trying to find out where the least distortions are to make your data look the best. It's nice to put data onto these projections to reduce those distortions, and also it gives you a single coordinate space for working with multiple instruments, multiple data from different sources. So you may get one that's from one projection, you may have random latitude longitude points, but you want to combine all these together. Maybe the sphere of the Earth isn't the best way to look at that, so let's try some projections. Let's start peeking into this concept with SatPy. We're going to start with our first code cell loading channel 6. Everything's the same as before, same reader, just loading channel 6 this time. I'm going to talk about that area definition again. So if I print out this area definition, we see things like identifier names like goes east. We have a human readable description talking about this is a 2-kilometer resolution area. So this is the geolocation, or geolocation of the data we're looking at. So our data is an image on the Earth. Where is it on the Earth? How do we describe that? The way that SatPy is doing that is through this area object. So we have these names. We have things like how many pixels are there in columns and rows. We have this area extent. So this is saying where is this, so this is lower, or this is the leftmost coordinate of our square. This is the bottom of our square. This is the right side, and this is the top. So those are metered coordinates, so that's telling us where our square of our rectangle of data is in this XY coordinate space. This projection here, you don't have to know what every parameter is, but just know that like there are the different shapes that we can choose here, we can specify the different shape, we can specify how big it is, what that shape of that cone is, all through these parameters. Right here, SatPy is using parameters from the Proj C library. You may have also heard of well-known text, or WKT. That's another way to describe these parameters. So by changing these parameters and what their values are, you can change what that shape is and what your end distortion is and what you're looking at. Here, one of the key points here is that the proj parameter is set to GEOS. That's short for geostationary. That's the type of projection this is. It looks something like this image of the Earth. I have this little link here, I can open that. This is the proj library's description of this projection. This is where I took the image from. So we can see that this image of the Earth is described by this string of parameters. In SatPy we were using a dictionary, but it can be represented as a string. So there's all this math that goes into it, all these parameters that we can change, but the end result is that we have an image of the Earth. And so you can imagine, if you are the satellite looking at the Earth, this is what you might see. So this is how we use this with geostationary data or gridding data in general, is that we have this image of the Earth. If our data was something on a different projection, like Lambert conformal conic, we can click on this link too, bring up the proj description. So we get this image, it's described by these parameters down here, and we get a different image. So different distortions, different amount of what we're looking at, and what we're trying to do is describe in this image, where is our square, where is our rectangle of data? We need to describe that so we know every point. If we could use latitude, longitude points for every pixel, but then that means we have to hold those into memory as we pass our data around. If we have something like this area definition, we have some strings describing it, but we have this dictionary, we have this 4-element tuple, and we have the number of rows and columns, and that's all we have. That fully describes where this data is on the Earth, or in this projection. So, saves memory, saves computation time. Let's go a little further and look at the differences of some different resolutions. So we're talking about our image being on one of these projections, where it is on the Earth, but there are different numbers of rows and columns for the different bands because they're different spatial resolutions. So if we load channel 5, and we already had channel 6 loaded, so if we look at the two areas, we can see that the columns and rows are different. So channel 5 has twice as many rows and columns. Its area extent, so where those outer edges of the image are generally the same, relatively the same. But most importantly, the projection information is the same. This is because these are recorded from the same instrument. The data is on the same projection. That means it's on the same coordinate system. So x equals 1,000, y equals 1,000. That point is the same in the coordinate systems for these data. Now, so I mentioned we have two data arrays. They are different sizes. So how do we do some calculations with those? You would have to make them the same shape so that you could actually work with them. The easiest way to do that in SatPy is to resample. There are many different resampling algorithms, and we'll step through some of them here. The most basic of which is native, which is technically not resampling, but it makes the most sense in the interface of SatPy to put it here. So we can call scene.resample with the resampler native. It will return a copy of the scene with this resampling applied to it. So let's run this cell, and I'll explain a little bit about this. So the last line of this cell is saying, are the channels the same shape now? Do they have the same number of rows and columns? And that's true. What native resampling is doing is it's saying, by default, what is the highest resolution channel we're working with? How do I make the lower resolution channels the same resolution as the higher ones? The easiest way to do that is replicating pixels. That's why native resampling isn't technically resampling, but we're making things the same resolution. It's close enough for a lot of work that we do. We can verify that everything is the same by looking at the area attribute of channel 6 again, and now we have the same number of rows and pixels, or rows and columns, as our channel 5. So, let's say we wanted to plot a difference. Now that things are the same resolution, we can actually do that. Our arrays are the same size. So we're going to load Matplotlib, And we're going to treat data arrays just like we would if we had NumPy arrays. So we're accessing the scene object, getting channel 6. We're subtracting the channel 5 data set. And notice I'm using the new scene variable that I got here. This was the one that resample returned. So I have this new data array diff. I use the Xray plotting utilities. And running this, I get a plot. So I now worked with data that was at different resolutions that I couldn't do before. So like I said, native resampler will it will replicate data if it needs to. So this pixel is a fourth of the resolution of the destination that we want. So we will repeat the pixel 4 times to make them the same resolution. So that's one way we can resample, make things the same resolution. But what if we wanted to change the projection? We can use a different resampling method for that. We can use nearest neighbor resampling. But to start with that, we have to actually have an output area, an output projection that we want to go to. We can use the PyResample libraries, create area def. So this is like if you wanted to change the projection but affect distortion, and again, you want to change the some projection parameters, maybe you want to cut out a specific area of the data that you're looking at with a different projection. So we can use this create area def to define those distortions, well, not the distortions, but define the projection and the parameters of that projection, that area that we're looking at. So I'm going to import this, and then you can put a question mark at the end of anything in a notebook, an object, a function, and it will give you the documentation. So this open this little pop-up window for me, this little pane, and this gives me the doc string for that function. If you want to, you can look at all of the different parameters that it accepts. I'm going to close that by hitting the X in the upper right. So what this function is trying to do is you give it some set of parameters for describing this area, and it will figure out what it has to do to make a valid area definition for you that fully describes that area that you're trying to make. So here I'm calling it with a dictionary of some projection parameters. This is just when I grabbed and wrote. I'm saying I want a 1000 by 1000 image. Area extent, we've talked about how this is in meters. If somebody knows how to magically come up with those meters, that's amazing. I do not know how to do that. I typically work with degrees. I know where things are relative to latitude and longitude. So I can specify things in degrees by using this units keyword argument and saying degrees. That means any number that represents some distance in here will be in degrees, some coordinate. So area extent here, this is the left side of the image, and then we go to the bottom, the right, and the top coordinate. So these are longitude and latitude values. So if I run this and I print out what that area definition is, we see I have the projection that I asked for, I have the rows and columns, and then create area def did the conversion of the meters for us using the proj library to transform those coordinates for us. Now we have this output area that we're trying to get to. So we defined a new number of pixels. We can pass this area definition to resample. By default, it will do nearest neighbor resampling, and we get a new scene similar to what we did before. I should have pointed out, I think these cells are out of order. As part of this area definition, we're also defining a resolution. So we defined number of pixels, but the other side of that coin is there's a resolution for each of those pixels. So we can use these attributes on the area definition to say that, in the X dimension that they're about 1,500 meters, it's about 2 kilometers in the Y dimension, tells us the resolution of our output area. Going back to our resampled area, if I plot channel 5, this is after the resampling, we'll see that this took a little bit longer, but we now have a smaller area. We have, it's a different resolution. I can tell you it's 1,000 by 1,000 pixels. It kept all of our attributes because we can see that our color bar has, let's spread this out a little further. Our color bar has its label. We have our axis labels as well, but we're at a different resolution, different size, different projection, and that all happened with that resample call. I don't know if I have, Yeah, so we could look at the data array that's produced from that. We'll do that next. Yeah, are there any questions so far before I move on to the next part of this?
Where was the nearest neighbor resampling specified?
So
What changed?
it is the default, so you could also do it here by doing resampler equals nearest. But that is the default. Before, what I did when I did native resampling is I did resampler native, and I didn't specify anything there because the default area will be the maximum resolution of whatever channels we're looking at. Yeah, so that would return the same results. So far we created an output area definition with everything specified. We gave it enough information to tell it what projection, what size, all of that information. But what if we didn't know everything right away? What if we wanted to say, we have the projection, and we know we want 5 kilometer resolution of our pixels, but we don't know where our data is. Just make it work. Just make an image that shows all of our data. We can use that same create area def function, but not provided all of the information, and it will create what's called a dynamic area definition. A dynamic area definition doesn't have all the parameters filled in, but they will be filled in by the resampling method when we call it. So let's create this area definition. It's the same projection as before, but now I've specified a keyword argument saying 5 kilometer resolution. So that means in the X and Y dimension, I want both of them to be, I want each pixel to represent 5 kilometers on this, this projection. We pass this area to the resample method, just like we did before. This will default to the nearest neighbor resampling, and we can print out the shape of our area. Now this is going to take a lot longer than the last resample. That's because it's actually figuring out, based on the longitude, latitude points of our input data, what it needs to create as far as the area definition is concerned. And so we can see it decided that based on the projection, the resolution we want, and where our data is on the Earth, the best size for this output area would be this many rows, this many columns. We can now plot this. And this is actually going to do the nearest neighbor resampling that we prepared using Dask. So we built up those calculations, everything from loading to the file to scaling it out of the file to doing the actual nearest neighbor resampling and then plotting the data. All of that happened and was computed by Xray technically when we did this plot. So we get this image. So this is what that GOES data, that ABI data looks when you transform it from a geostationary projection to a Lambert conformal conic projection, and you tell it to look at all of the data. We mentioned earlier when we were looking at this data that that top left corner was in space. That's why we have this long arm going off on the upper left, because in the projection, that data is actually going off the Earth, and the projection doesn't have a place to put it. The data also has some distortions up there because we're going from one projection to another, and in this projection, these pixels are really far apart. And so by default, the nearest neighbor's choice of how far it looks for valid pixels was not enough. So we get this kind of separation. So I guess if I use the zoom tool, and we get these cool artifacts. Cool. So that's something you have to worry about as far as how far do I tell the algorithm to look. There are a lot of options for resampling. There are different resampling algorithms, but that's where we go as far as this is how we do that as far as changing and transforming projection or data from one projection to another. All right. Any questions now? No. All right. So what I would like you to do is take about 10 minutes and play with, I have some cells started here where we're creating an area definition, we're resampling, and we're plotting it. We're using channel 5 for this whole time. I give you some suggestions for what projections you could try. We are looking at a relatively small area of data, so the distortion is not very large, I will tell you that. But try these different projections in this create area def, change some of the parameters, maybe the area extent. Feel free to look at the other parameters that create area def can accept. Try resampling, see how it affects things. If you come up with questions, feel free to ask. Remember, we have some helpers, so raise your hand if you have some problems, and we'll see where we can go from there. So let's do 10 minutes just to play around with the projections. All right, I think I'm going to cut this a little short just so I can show an example that came up from a question. The question was, I have Mercator, but why are the coordinates in meters? Mercator is an actual metered projection. It just looks a lot like a lat-long grid because it's a cylinder and we're expanding that cylinder. So it looks a lot like a lat-long set of degrees. If we wanted to do degrees, we can do long lat here for the projection. That's part of the proj library. I'll remove this lon 0. Everything else I'm going to keep the same. I want it 1000 by 1000. I want the air extent to be the same. I run these same resample commands. I get a plot, and we can see that my x and y are now in degrees because I'm in a long lat projection, or lat long, however you want to say it. Yeah, same thing though, extents, coordinates are in degrees, and that all worked. Anybody have any questions based on what they saw or anything else?
When you say the pixel size is so many meters, I mean, depending on the projection, different pixels are different sizes. So what does that actually mean?
So the question is, what does resolution mean? Because the resolution is different in each projection. And
Well, I mean, it's different for different pixels in each projection.
yes. So what we're defining is a grid of pixels in a particular projection's coordinate system. So with this projection, we're defining where in that projection, where in that shape, where is 0, 0, where is our origin of our xy coordinates, and then from that origin, what are the coordinates of each of our pixels for our image. We're saying that in that projection space, in that number of, in those coordinates, how wide are each of our pixels, how high are each of our pixels. Those meters are based on the projection parameters and the size of that projection, and how that coordinate system that we've defined, what a meter means in that projection. Generally, it's representing a meter on the Earth at the best location, at the best reference, where there's no distortion. So 750 meters in the geostationary projection is not 750 meters in a different projection, but we're defining this grid that is equal distance between each pixel in projection space, not on the Earth, but in projection space. So depending on which projection we choose, we get different distortions based on those distances. Does that kind of answer that? No?
I get the idea that it's complicated.
Yeah. I could say it.
Basically, it's the resolution at the least distortion. So like if I have a lot of distortion at the edges and the middle is least distortion, and that's where I get my on the ground 750.
Yeah. Like if you were going over Austin, Texas, and you changed like this lon 0 and these lat parameters based on the definition of what that projection means, that projection has some definition of what location has the least amount of distortion. Typically, it's somewhere like where this lon 0 is and wherever your lat parameter is. That's your reference. So that's supposed to generally be the least amount of distortion. So that should be where you have a one-to-one correspondence between the distance you're defining, so that pixel resolution, and what's actually on the Earth. But as was mentioned in the definition of map projections from that book, depending on which projection you're looking at, you're not always maintaining distance between the projection and actual Earth distance. Sometimes you're maintaining the angle or the area of something. Yeah, so yes, complicated. There's some math that happens and then some things happen. Yeah.
Do you generate like a heat map of the distortion for that projection?
That is, I'm sure you could, and I think people, actually, I think Wikipedia does that. Wikipedia, projection, Mercator. Randomly searching Wikipedia. That's just a good idea. So this is the Mercator projection was deformation. So this, I think all the Wikipedia pages have things like this for these projections, trying to show what amount of distortion is. There are people in this room that know much more about this than I do. But in general, so as an explanation of this, this is a cylinder over the Earth. And so if you imagine you have that globe and you're spreading out onto the cylinder, you're projecting onto the cylinder, you have much more distortion at the higher latitudes because of how far those pixels have to spread. This to understand this at all requires some good amount of 3D visualization in your head. At least that's the way I understand it. But yeah, there's a lot of math and complex stuff. Yeah.
Is there a good method, function, or way to use in order to calculate that like arc distance, right? So to normalize the meter or the distortion?
Short answer is I don't know. What I typically do, normally I'm told by whoever I'm working with what projection they want their stuff in. So I get around it by doing that. Otherwise, I have projections that I typically use for different areas because I've been told or have had some level of experience where I know that there should be less distortion at this location. But yeah, beyond that.
Supply different imagery.
Yeah, like mid latitudes, Lambert conformal, conic does pretty good. Mercator's pretty good for things at the equator because you can see it's all the same level of distortion there. Anything near the poles, you might want to use a polar stereographic. So I typically stick with those three projections. Everyone has their own little thing about why they choose the projection. People come up with new projections all the time because they think there's less distortion. Yeah, but we're getting to the point where I am not an expert.
I was more curious about the dynamic areas.
Yeah.
Getting some introspection on those might be helpful. To see like, do a heat map that shows like for these pixels, 1 meter is equal to a meter. And then changing as a meter becomes more or less.
Yeah. So for dynamic areas, the question is introspection on how it's doing what it's doing and what other options would there be. It is definitely maybe not the simplest approach to doing it, but there is some stuff like if we have this projection, we know that it's very strange, so we need to do completely different calculations to estimate things well. It's dynamic areas are very give me your best guess. I don't know if there's an overall goal in the algorithms that are involved with that. Like what are we reducing as far as distortion or size and that kind of thing. And it also differs on what parameters you provide and what you want out. Okay, let's take a 15-minute break and get back here around 10:20, let's say. Feel free to ask me questions. I will probably be around here. So talking with Jeff, our helper, one of our helpers during the break, he brought up a good idea for explaining this distortion and this resolution better. And I can only think of doing it with hand gestures because I don't know if anybody would see it if I drew it on the board, and I'm not very good at drawing anyway. So if we think about the geostationary projection, what we're doing is we have our sphere, our Earth, and we're putting some piece of paper, some graph paper on top of that Earth, and we're projecting whatever's on the Earth onto that piece of paper. When we're talking about area definition resolutions, we're talking about the distance on that piece of paper, not the distance on the Earth. And so the distortion is the difference between the distance on that piece of paper when it's projected back onto the Earth. So what is the difference between those distances? So yeah, so when we move So when we have this pixel and the next pixel is 500 meters to the left, that's 500 meters on that piece of paper. And Jeff pointed out that this image that I showed, if I can make it bigger. So this is from Matt Gunshore with SIMS, which is at the Space Science and Engineering Center at the University of Wisconsin. So this is that GOES ABI sector, or what it sees. And so we have the different sectors defined. The colors on this are the approximate pixel area on the Earth, if I'm understanding it correctly. So within this dark blue circle, these are supposed to be like a pretty good 1-to-1 ratio-ish. But as we move out, you can imagine the Earth is curving, but we're still representing it on a flat piece of paper. So there's more distortion between what 1 kilometer on our piece of paper represents on the Earth, or what it's actually seeing. So you get some curving effects. So we're going to go back to resampling, moving on to other things to do with resampling. And we're going to talk about our first polar orbiter satellite. So the polar orbiter instrument we're dealing with now is VIIRS, V-I-I-R-S. There is a VIIRS instrument on 2 satellites, SUMI NPP and NOAA-20, also called JPSS-1. Those, like I mentioned, are the polar orbiter satellites. So throughout the day, they're going from pole to pole as the Earth orbits. The instrument ends up seeing the entire Earth in strips of data. So I had you download some data from VIIRS, from the NOAA-20 satellite that is seeing this fire that we've been looking at with ABI data. So that's what this scene creation here is looking at. And so we're going to create this scene and use it like we did the ABI data. So we're going to ask what data sets are available. So we see a couple things. We see a list of some angles, satellite and solar angles, some longitude and latitude, and 2 data sets called IO3 and IO4. So these are the bands of VIIRS, two of the bands of VIIRS. VIIRS has 21 bands, does that sound right? It has 2 main resolutions of bands, so it has I band or imagery resolution bands. It also has M band or moderate resolution bands, but it follows the same kind of concept with ABI, where each band represents some wavelength, or it's measuring some wavelength, and so we get that same type of information. With VIIRS data, with polar orbiters in general, you usually get more channels on them. And you also get higher resolution channels. So let's start out by looking at the IO4 band and looking at some of the properties of that band. So we're going to use the load method like we did with ABI. We're going to look at IO4. So here we see we have a data array again. We have a Y and an X dimension. One thing you should notice is that this data that I'm showing you is one small chunk, I believe, of just about Texas. And we already have 7600 by 6400 pixels. This is showing you how much higher resolution polar orbiter data generally is compared to geostationary. Again, it's lower to the Earth. It's easier to get a higher resolution without having to go as far. We have wavelengths associated with this. This is a brightness temperature band that we're looking at, start time and end time. We have an area. It's slightly different than the area we dealt with before, and I'll explain that in a second. What else? So I bands from VIIRS are 375 meters per pixel. M bands are 750 meters generally. And there's another band called DNB, or day-night band. We won't be looking at that today, sorry. What else? So that's VIIRS. VIIRS being a polar orbiter, and the way it actually operates, the data is not gridded. Each pixel is not the same distance apart. We have to have a latitude and longitude point for each pixel to know exactly where it is. It's still the same idea that we have a coordinate for the center of the pixel, and we know generally what size it should be, but we're going to simplify it and say that the resolution right under the instrument, where that satellite is moving, right under the instrument is one resolution, and we're just going to pretend that it's the same resolution throughout. That's not true, but we're generally going to resample the data so that it doesn't matter. And we'll see why in a second. Yeah, let's look at the data. I can explain this more. The area for the VIIRS data is a swath definition. It's just like the area definition as far as its purpose. It's meant to define the geolocation where this data is, but because of the properties of the instrument, it's holding on to a longitude and latitude array. If we do get lon lats, we get a dask array, full size of the original image, and we could use it like we would longitude and latitude data. If we plot this data, so that PLT figure, we create a new figure, we use the Xray utilities. This is going to take a little bit. So we get some data, but it doesn't look very good. Two things you should notice. One, our data is flipped horizontally. California, Baja California is on the right side of the image, and Texas is on the left side of the image. This is just coming from how the data is stored in the file and how the satellite is orbiting the Earth and whether it's descending or ascending, just what the satellite is seeing. The white pieces on the side, I'll try zooming in and see if this makes a little sense. Oops. Maybe. Okay, you can kind of see it. So the way the VIIRS instrument works is by scanning the Earth. So as the satellite is moving or orbiting around the Earth, it will do one scan of some amount of rows, but it'll do one scan. The satellite is still orbiting, it does another scan, still orbiting, another scan, and you end up with a little bit of overlap on the edges. Just because of the way the Earth is round, it is not flat. As you go out, what you're seeing expands, so you have, you're basically seeing a tight set of pixels here, and as you go out, you're seeing more and more with each pixel that you're recording. You're seeing more of the Earth just because of the curvature of the Earth and the way the instrument is scanning. For each scan, you end up overlapping just a little bit. And these white parts of this plot of this data are called bow tie deletion, or the bow tie effect. And that's because you can imagine it kind of looks like a bow tie as it expands out. And so this is a processing software feature, I guess, where you don't need to have those duplicated pixels. So they will remove those pixels and send the data down to Earth from the satellite, but they don't have to send as much down because they know it's duplicated. So it's a compression kind of thing and saving transmission, but you get this effect. So if we look at the whole thing again, so we have this bow tie effect on the edge. It's not what we want to look at. We have latitude and longitude points. Our raw array does not look like what we expect the Earth to look like. The way we can resolve that is by resampling. So we're going to use the my area that we defined before. So mine is LCC. This is what it should be for everybody. So my area, it's an LCC projection. We see that here. It's 1000 by 1000. It's got some extents. We're going to call resample the same way we did with the geostationary satellite, but we're going to do polar, or this is a polar scene. We're going to hit resample, and we're going to plot. And now this is going to take a little while because we're going through each pixel of the polar data, trying to find out what, well, I guess I should, technically, to be correct, we're looking at each output pixel and saying which input pixel is the closest to this output pixel. And what we should get, this is one of the few places where the speed of your machine actually matters. Hopefully this should finish. What else can I say about this?
What's the bottleneck?
Thank you, Matt. Right now, nearest neighbor is using a KD tree. KD tree requires that you put, I A KD tree is a structure that lets you query for, at least the way we're using it. I have this coordinate. What is the nearest coordinate in your tree to that location? And so it will look through the tree using standard CS tree kind of things and give you some value back. So one bottleneck is that we have to create that KD tree, and we can't use Dask's ability to do things in parallel, at least with the way the algorithm's written right now, because we have to build that KD tree out of every pixel. We're not making any assumptions about where our input data is as far relative to each other, every other pixel. So we build this huge KD tree, and then we can pretty quickly query that tree to find the output pixels. So it is mostly that we have to, up to this point, Dask is doing things in parallel. We get to resampling, and we say, nope, we have to do everything, one thread, all in memory right now, and then we can split it up and do calculations again in parallel. But yeah, we have to hold that whole thing in memory. There are pull requests sitting right now for PyResample with algorithms that do this better. Things like knowing that this pixel in my input data is geographically right next to the pixel next to it in the NumPy array, or in the array, so we don't have to look at everything. The other thought that we had was doing a KD tree of KD trees, so we can build those KD trees in parallel and know whether or not we need to use them later on. Thank you, Matt. So, plot finished. We have our XY meters, as we did when we did geostationary data. One thing that is hopefully obvious is all of the white space in this image. This is the same my area that we used before with the ABI data, but we have a lot of missing space. There's no data there. And in fact, this is the only data I could find for VIIRS, for the VIIRS instrument, that covered this Texas fire during the duration of the Texas fire for 4 hours. This shows one of the major downsides of polar orbiter data is how long it takes to get another pass of that satellite over the same area. ABI, we talked about, it has some sectors that it's viewing every minute. It's taking data every minute. This, I have to wait hours to get another pass. And even though there's two VIIRS instruments in orbit right behind each other, this was the only data that I could get that had any bit of the fire in it. We can actually zoom in. There's a little yellow pixel right here.
No.
So there's the fire in Texas. So let's see, what do I have next? So to explain more about these pros and cons, so geostationary, we have high temporal resolution. So we have data every 1, 5, 10 minutes with ABI. We have lower spatial resolution generally with geostationary satellites. So the highest resolution for ABI was 250 meters, and that was one channel. For VIIRS, we have 5 channels at 375 meter. Another con right now of geostationary satellites is that they generally have less channels, less wavelengths that they're looking at. What else? Yeah, so with that temporal resolution, you can see as atmospheric events, meteorological events, as they evolve over time very easily. VIIRS, polar orbiter data, you have higher resolution. The satellite is closer to the Earth. It's easier to see closer. You generally have more bands. You get a full coverage of the Earth. Geostationary, you're only seeing one part of the Earth because the satellite is not moving. But it takes more time to get that full coverage or to get an image of the same chunk of the Earth. So that is the quick and dirty introduction to polar orbiter VIIRS data. Any questions on that so far? Okay. So now something you might want to do, and this is really depends on what your area of science is and what you're trying to do with this data, but this is a very simple proof of concept of we have ABI data, it's showing something. We have VIIRS data, it's showing something. How do we compare the results from these different instruments? Maybe we want to make sure that they're seeing the same thing. Maybe one has one wavelength for a channel that the other does not. But the way we have our data when we're starting is the ABI data is on the geostationary projection. The VIIRS data is lat-long coordinates. It's not technically on a projection. So how can we compare these? Well, this is the resampling lesson, so we're going to resample. We're going to create two separate scenes, one for ABI, so we're going to call that ABI scene. We're going to load channel 5 and channel 7. One thing I should point out here, if I'm remembering correctly, this ABI data is from the mesoscale, so those are those 1-minute sectors. That was one of the reasons I chose this fire, is that one of the mesosectors for ABI was over the fire. Yeah, I didn't mention that. They can move the mesosectors for GOES ABI. So if there's a hurricane, we can look at the hurricane and get 1-minute data. Oh, there's a fire in Texas. We're going to move it. We can watch Texas. Yeah, so this is mesoscale data. We were looking at CONUS, continental US data, so that was a larger area. We're now looking at a smaller set of data. Next, we're going to load a VIIRS scene. So we're doing the VIIRS SDR. I believe, just based on my file pattern, I'm loading slightly less data. But we're going to load IO3 and IO5. And let's print out some information from these. So we're going to print out the start time and the size of these arrays. So ABI, the data that I have that's closest to the VIIRS data, is 8 seconds different from the VIIRS data as far as start time. You can see that the ABI data, even though it generally covers the same geographic area, it has many less pixels. Let's see what else. These bands do line up, so do I have this somewhere? So channel 5 from ABI and IO3 from VIIRS are the same wavelength, and channel 7 from ABI is about the same wavelength as IO4 from VIIRS. So we're comparing two near the same wavelengths. We're going to move on to this big chunk of code. So what we're doing here, and actually let's start this, so run this and I'll explain it. So we're using Dask's progress bar again, just to see see where we are in processing this. This first line inside this progress bar, we're creating a new scene. We're taking the ABI scene and we're resampling. We're using the native resampler. This is because we want to do this because channel 5 and channel 7 are different resolutions. We want to make them the same resolution so that we're comparing the same thing. NumPy arrays are the same. We're going to skip down to the VIIRS part for a sec. VIIRS, we're going to resample, and I'm going to pass in this new area definition that we haven't used yet. We're going to take the maximum resolution area from the ABI scene and resample VIIRS to that projection. So we're taking VIIRS lat-long data and resampling it to the ABI geostationary projection. By doing that, we're making them on the same projection, same resolution, same size of the arrays, and so now they are comparable. The other key part of this is I'm using this fancy Dask persist method or function, and I'm giving it these data arrays. What this is doing is, we talked about how Dask is building up these tasks that it's performing. We want to do, if we were to plot the results of this resampling, it would have to recompute everything up to this point. Every time we replotted, every time we wanted some result, it would have to recompute that every time. This is a long resampling process. We see that to resample the VIIRS, it took 24 seconds to do it the way we did it. Persist is saying, I want you to do all of the computations up to this point and then hold them in memory. Still treat it like a Dask array, but compute everything up to this point. So now everything that we do in the future with this data is starting from that starting point, that checkpoint that we made. Rather than having to compute everything, loading things from disk, we're starting from here. This will save us in the future operations so that it doesn't have to take 24, 25 seconds every time we want to do something. So now that we've done this resampling, let's use those new scenes that we got. We're going to access those channels and plot them using the same Xray plotting utilities that we had. So I get channel 5 that looks like this. Okay. And plot IO3. And so you can see how fast these were. where before when I was plotting VIIRS data, it took quite a while. That's because we persisted the data into memory. So some things to point out. I might have to make this smaller resolution for. Okay. So you can see the colors are a little different. You can see that the VIIRS data doesn't fully cover the area that we've defined, so it doesn't have the same coverage as the ABI data. But yeah, you should see that the shades of the colors are slightly different. So let's say we wanted to take a difference of those channels. We know that they're the same resolution now, so we should be able to do that. So let's take 10 minutes and use what you know about Matplotlib plotting these data arrays, knowing what you know about treating data arrays like NumPy arrays, doing basic arithmetic. See if you can create a plot for each of the differences here. It's less scientifically useful, I was told by one of the scientists at my work, but if you finish that quickly, you could do the average of two of the bands. The other thing you could try to do, if you're feeling adventurous, is instead of resampling the VIIRS data to the ABI projection, you could try reprojecting to a new area definition that you define with a higher resolution. Right now, we've kind of negated all of the high resolution-ness of the VIIRS data because we've put it at a lower resolution. So anyway, take 10 minutes, see if you can create some plots. There are solutions there, just don't cheat. And we'll talk about that in 10 minutes. I'm gonna bring us back a little early. I'm a little worried about time. You should get an image like this for your first plot, channel 5 minus IO3, if that's the way you chose to do that difference. I set this color map here, this red-blue one, just to show the difference. I limited the color bar from -25 to 25 Kelvin, because these are brightness temperature bands, so they're in Kelvin. You would expect things that are at the same wavelength to have generally no differences, but we see quite a few here. A lot of them are on the edge of clouds, especially if you look at things like where this fire is. You have this big dark shadow. One reason for these differences, the data was not recorded at exactly the same time. So you have slight shifts just from things moving and the satellites moving. And then the other main reason is that these satellites are not viewing the Earth from the same spot. Not only just height of their orbit, but one is over here and one is over here. And so you see different sides of shadows and clouds, and so you just see things from a different angle. So there's differences. So to summarize what we did right here, we took data from two different instruments that were on completely different projections or not even on projections. We resampled them and compared them fairly quickly in, 5 to 10 lines of code. This opens the door for us to compare satellites, or compare instruments from different satellites, or compare instruments that are on the same satellite. So right now we've been looking at ABI, or we've been looking at VIIRS, but there are other instruments on the satellite that VIIRS is on. So they might record data in different ways, different resolutions, different locations, different scanning patterns. Sometimes you get some weird ones where they spin halfway through their scanning pattern. So by resampling, we're able to put them kind of on the same domain so that we can work with them together. And that's that for that part of resampling. Because I'm worried about time, I'm going to go pretty quick through this next part. Let's say you wanted to cut out a specific chunk of your data without having to do this complex resampling step. Or what if you didn't need to do all of the processing of every pixel, you just want a general idea of what the image looks like. SatPy comes with some methods for helping with that, and you can act on the scene as a whole. So we're going to create an ABI scene again here. There is a crop method on the scene. We can specify a bounding box, just like we've been doing with the area extents. In degrees, we can also specify XY if you want to do that, or you could provide an area and you want to say match to this area. If we do this, it quickly returns a result. We have a much smaller data array, so we can plot this as we would. and we see we have a much smaller section. I hard-coded this so that it shows the fire. But yeah, so this didn't have to do any of the resampling steps. It didn't have to do nearest neighbor at all. It didn't even have to replicate pixels necessarily. It just cut out the section of the data that we wanted based on the geolocation. The other method similar to this, if we didn't want to look at every pixel, we just wanted a general idea, is we can aggregate data. So by default, this will average data by dimension. So we can say ABI scene aggregate every 10 pixels in the Y dimension, every 10 pixels in the X dimension, and return me a new scene with that average. So if we do that, we get 100 by 100. Our original was 1000 by 1000. We plot this, we can see it's much more low resolution, a lot of jaggedy edges here. One interesting thing is, I believe we're looking, yeah, channel 5, you don't really see anything from the fire. That's because it's averaging every 10 pixels. If we wanted to take the maximum, we can provide a different function that it uses. Underneath the aggregate function, it's using Xray's new Coarsen function. New-ish. So here we did the maximum instead of the mean, so now we can see those bright fire pixels from that fire in Texas. Before I move on to the next lesson, any questions on resampling?
When you do the averaging, do you normalize it all for the size of the pixel? Like, I work with level 3 data, and so the pixels at the closer to the poles are a lot smaller in area than the ones at the equator. So we normally normalize by the cosine of the latitude.
So the question is, do we normalize based on the size of the pixel? For example, as you go further or higher in latitude, your pixels might stretch or represent more data. We do not, I did not write this function, but it's using Xray's Coarsen, which I believe is doing everything just on number of pixels. And so if your data is not already normalized, it is not doing that. Yeah.
Is this resampling that's being done here, is that part of DASC itself, or is it using the GL library?
These are custom algorithms written in available through the Pi resample library, which is through PyTroll. Back when these were written, access to the Gödel resampling algorithms was not easy from Python. And it also, back when we started, had trouble dealing with non-gridded data. So dealing with like those VIIRS swaths, it didn't really handle that they weren't uniform distances. So yeah, they're all custom in Pi resample right now, but yeah, the idea is to expand and use Gödel's interfaces when we can. Okay, all right, let's close out resampling. During the exercise, I was looking up other projections in Wikipedia. So you have some strange ones. Yeah. Just whatever you want to do. Okay, so I'm going to kill the resampling lesson. I'm going to load the lesson 5 composites. Let's see, just remind myself how long this is. Okay, let's see how fast we can get through this. Okay, we're going to now work on another common step when working with satellite data, which is to make RGB images or combine bands in different ways to make something new. So we kind of talked about how you might combine different wavelength bands to figure out what type of clouds there are. A more simple form of doing something like that is making an RGB image. So RGB images have 3 values per pixel. You have red, green, and blue, represents how much of that particular color should be in that pixel. And when you do that, you get a nice color image out. Now, what we can do is set all of the red values to a particular channel, all of the green values to a particular satellite channel, all the blue to another channel. And by doing this, you get particular features that a wavelength picks up end up being a certain color in your output image. So let's look at a couple of these. So we're going to look at the ABI CONUS data again. Same setup as always before, except we're going to end this cell by asking the scene what available composites are there. So we get this nice long-ish list of various composites, various variations on those composites. These are all built into SatPy, and they're things that either the contributors or the developers have been playing with, or they're semi-standard by some organization, some space organization, and they might publish these in their papers and say, we have this new satellite, here's how we combine these bands to make an RGB, and this is the results. And so they'll bring up this recipe of, we took this channel, we set it to red, we took this one, set it to green, and this is what we got. RGBs are used by forecasters a lot because it gives you a quick way to see, I guess, the state of the atmosphere. If you're trained at looking at these RGBs, you can say, oh, I know that yellow is going to mean this in this particular RGB. So we will see an example of this by looking at the air mass RGB. The air mass RGB takes for the, and this is going to get confusing because I'm going to accidentally say channel when I'm referring to the red component of the image. So I'll try to keep it straight. The red component of the image will be the channel 8 minus channel 10 data. The green component will be channel 12 minus channel 13, and blue will be channel 8 by itself. The EUMETSAT, so that's the European organization, their training material talks about air mass and how it involves water vapor channels. And so the main applications are the detection of dynamic processes such as rapid cyclogenesis, jet streams, and potential vorticity anomalies. I don't know what that means. I'm not a scientist, but it shows stuff. That's as far as I'm going to go with that. So we can take these composite names that are pre-configured in SatPy and ask for them in the same load method that we've been loading our channels with. If we run this load method, we can see it returns relatively instantly, and we have a data array as we had before. The main difference here is that we now have a bands dimension, and it's got a size of 3. If we look at the coordinates, we can go to the next cell and print out the coordinates, so we can do dot coords. That gives us access to those coordinates. We can print out bands. Bands itself is a data array with values R, G, and B. So this index in this array represents the red component of the image, and so on. We can save this just like we did in the writing lesson. It's treated just like any other data array, so I can write this as a PNG. We'll see that it takes a lot longer than it did, well, relatively a lot longer. So I can go back to my file browser, I'll find an air mass, and this is what air mass looks like. So this is a lot more interesting than looking at, well, depending on who you are. This is a lot more interesting to look at just because it's more colorful, but this isn't a color map. This isn't VIIRS or Magma or whatever Matplotlib color map. This is, the colors are determined by the data from 3 separate bands, well, in this case 5 separate bands. And so you can imagine forecasters being trained on this and saying, okay, well, red, I know that red represents that there's this state of the atmosphere, green is this, and so on. So, moving on. There's a little bit of extra added complexity when trying to plot this stuff with Xray because what we tried to do in SatPy is for these composites, for these RGBs, keep the temperature differences. So for that red component, we want the actual temperature differences. But when we save it to an image, there's typically these color limits that they have. So they say everything below this difference should be clipped. Everything above this difference should be clipped. That goes into that enhancing step that I talked about, converting data values to image values, those 8-bit unsigned integers. So we're going to use a new function in this step to do that normalization for us, to do that limiting, called getEnhancedImage. If we do this with a particular data array, it will go through those built-in enhancements that SatPy has for doing things like this and give us this image object back. The image has a .data attribute. We're just going to kind of skip over that for now, but it gives us a data array back, and we can use the same Xray plotting utilities. So using that extra little step of getEnhancedImage and doing .data, we can tell Xray here that we're making an RGB and that the bands dimension is where those bands are located. We tell it that the data has been normalized So it should not have to do anything between, or anything greater than, or less than 0 or greater than 1. If we didn't do that, it would it would take the min and max of each channel, I believe, or as a whole. So anyway, point is, we get this air mass RGB. And we got lucky here. Lucky, I mean, I wrote it this way. Air mass is combining bands of all the same resolution. So we got lucky in that when we asked it to make air mass, it could do all those calculations. They're all the same resolution, they're all the same shape. Let's do the subtractions, and boom, we have an RGB. If we are compositing things of different resolution, the only way we know to do that is by resampling. So let's try to load a different composite now, the natural color composite. It's made up of channel 5, channel 3, and channel 2. But channel 2 is at a different resolution than the other channels. EUMETSAT's training materials say snow on the ground as well as ice over mountains, frozen lakes, and sea ice appear cyan in the natural color RGB images. So that's what people might use this to, might look for in this RGB. So we'll use scene.load again, call natural color, and we get this warning. It says the following data sets were not created and may require resampling to be generated, and it lists this big long thing about natural color. So this is telling us what I already told you, which is that natural color combines different resolutions, and it's not going to guess on how those should be combined. So if we actually check, we use that in syntax, natural color isn't actually in the scene even though we asked for it to be loaded. We can use a missing datasets attribute or property, and it tells us that this natural color is missing. And so if we wanted to generate this RGB, we'd have to resample, make things the same size. The simple way of doing that is using the native resampler. Here, instead of using the default of the maximum resolution area, we're going to use this min area, and we're going to call resample, and then we will see what natural color gives us. So now we actually have our data array. So we asked for natural color, we were warned it can't be generated, we checked the properties, it said yeah, it wasn't generated, it's not in the scene yet. We resampled, SatPy's scene said, oh, I know that you wished to have this RGB before, and I resampled, let's see if I can make this RGB now. It successfully did, and now we have that natural color data array in our scene. So same kind of idea with air mass. We now have a bands dimension set to RGB. We have some attributes filled in, taken from the channels that were involved, but also some extra added things by the compositing step of this. So let's use that same Matplotlib functionality, get enhanced image, getting the data, telling it that we're making an RGB, an RGB over the bands dimension. This will take a little bit longer. I made it so there's a progress bar at the bottom. Maybe should have started running this before I talked. So this is going through loading the data, doing that native resampling, doing the differences, combining them, and we get this image. So cyan is supposed to be ice and all that kind of stuff, and that's what we see. Yeah, so this is called natural color. This recipe comes from the EUMETSAT organization. Now, so far we've been working with built-in RGBs from that are built into SatPy. A lot of these are standard by some organization like EUMETSAT or NOAA, and they're the kind of RGBs that they make all the time and they give to people. That's why they're built into SatPy, because they need to be generated all the time. But let's say we are making up our own RGB. We want to this is actually an area of research for some people, is to figure out what RGB looks the best, what bands we can do to see different information just from the basic bands that we're loading from the data files. So we're going to do that now. So we're going to use the same CONUS image, but we're just going to start from scratch with the scene. If we list out the available data set names, we see we have 16 channels, as we did before. And now we're going to load 3 channels that we plan to use in an RGB. So this is up to you to choose whichever 3 you want. You might want to choose at least one of the reflectance bands, so I think that's channel 1 through 5, at least as one color, just to give some differences to it. So I'm going to do channel 7, channel 8, and then channel 1. And I'm going to load all those 3 channels. And then to do the compositing in a way where we're keeping attributes that we want, shared attributes, we're keeping the dimensions the way we want, we're also doing certain checks like making sure they're the same resolution before we combine them. We're going to use a built-in base compositor class called generic compositor from SatPy. So we're going to import it here. We're going to create it, and we give it a name, so we're just going to call it myRGB. I suggest you keep it as that name because we'll use it later. And then we call the compositor. So what this compositor is going to return is a new data array. We give it data arrays, it does the math and the combinations and the aggregating that it needs to do, and returns some new data array. So if we run this, let's see what we get. It's a big, long, ugly exception in Jupyter Notebook, but the important part to see is this part that says incompatible areas. So this is SatPy telling us resolutions are different, at least for mine. You may not have gotten this depending on what bands you chose, and that's completely fine. You can still follow along with this. Nothing will be wrong. But yeah, this is SatPy's way of saying, no, these aren't the same resolution. We need to do something about this. So just as before, we're going to resample. So we're going to use the resample method again, native resampler. I'm going to call the compositor object that I created before with the same bands, but realize here that I'm using the resampled scene, this new scene, and we'll print out myRGB. So just like all the other RGBs, we have a bands dimension, size 3, RGB, and the coordinates, and we have some attributes that the compositor figured out. Now we can use our Matplotlib stuff that we've been going over, saying RGB bands, and we get something out. One issue with this is that by default, SatPy said, I don't know what my RGB is. I don't know what UMetSat or whoever has defined as good limits for these values. I don't know how to make this good, quote unquote, as defined by these official recipes. So it took the minimum and the maximum of every component, red, green, and blue, and stretched the data linearly to fit that full range in our output image. So you have very bright values and you have very dark values. Mine doesn't actually look that bad, but we might want to control that. So since we're doing everything manually, what we can do over the next, let's say 5-ish to 10-ish minutes, we can take these calculations and rebuild our composite and replot it. Note that the numbers here are Kelvin in the first two for the red and green. The bottom one is the reflectances, and what we're doing here is a linear stretch between two values. So we have a minimum 220, and I use that twice in this equation, and then a maximum of 260. So if you take the next 5 to 10 minutes, play with these values, see if you can get a plot that looks kind of okay. And you can change, actually no, you should keep that the same. But yeah, so make sure that if you're using Kelvin, if the band you chose is a brightness temperature and reflectance otherwise, it should be kind of easy to tell once you plot it with the wrong values. Yeah, so let's do that for, let's say 5 to 10 minutes. See how people are doing. Let's bring it back. So this is what I came up with. I think I had channel 7, 8, and channel 1. Came up with some limits. There's some colors on it. I'm not going to look up what it actually means. But so far we had to do all of these steps manually. We had to import that compositor. We had to load the bands that we wanted to use. We had to set the limits. We might want to reuse this a lot. We might want to share it with somebody. We had a compositing step, and we had that enhancing, scaling, stretching step. SatPy allows you to define some YAML configuration files so that you can reuse this stuff or provide it to SatPy in a pull request as a composite that you think other people should have access to from the built-in SatPy. By default, it will look at what's in the SatPy library. It will also look at, there's ways to point it to a particular directory, or it will look in your current directory for a certain directory structure to find these YAML files. So what we're going to do now is edit these YAML files and
configure our composite in them. So down here, below the plot that you made, there's a section and it's got this YAML text right here. It starts with composites : if you could highlight that and copy it, we're then going to go to our notebooks directory. We're going to edit a text file, edit a YAML file, but we can do that through Jupyter Notebook. So I'm going to go to notebooks, in my notebooks directory, inside composites, there's an abi.yaml. So I'm going to click that, and it gives me this text YAML document. I'm going to paste the highlighted text that I had in here. And what we're doing is defining that recipe of what bands go into this composite. We did the generic compositor, so we're taking one channel and assigning it to each component of the image. So what you should do now is take this text and edit each of these channel names to say whatever channel you used. So I used channel 7 here, channel 8 here, and channel 1 for green. So yeah, that's an order, R, G, and B. So we can specify that in the YAML, and then you can save it. File save, and I'll just wait a little bit, make sure everybody's got it. When you get done with that part of it, if we go back to the lesson, below that text there was also an enhancements section. Starts with enhancements : I'm going to copy that just like we did before, but instead of going in the composites abi.yaml, we're going to go back to notebooks, enhancements, abi.yaml. And we're just going to paste that text in there, if I paste correctly. And here's where we're going to put in those stretch limits that we came up with. So I'm going to edit our min. I don't actually remember what I did for this, so I'm going to go back. So 220 to 300 I did, so 220 here, 300 here, and so on. So let everybody fill those in. 220, 250. And then also save that file. So we have created these YAML files that represent the RGB recipe that we've come up with over the last 10-15 minutes, specifying what channels go in, that's our composite recipe, and then specifying what the limits are. These YAML files essentially point to Python functions or Python classes that should be called, and gives them parameters to know how they should operate. If you looked at the source code for SatPy or in the repository, there are configuration files like this for every instrument. Some of them are defined for all instruments that are that have these wavelengths, so that we can reuse these recipes. So right now we listed every channel. We could have also listed what wavelength, just a different way to define these recipes so that we can reuse them later on, and that we don't have to type and copy this code everywhere. So because we are in the notebooks directory and this composites and enhancements directory are in there, SatPy will automatically find those and use them. So hopefully everybody has those defined, has those limits in there. And we can go back to our lesson. We can create a new scene, and we'll run that available composites name again, composite names. Everybody should see a myRGB now in that list. All right. So that tells us that we added that correctly to that composites configuration. Now we can use it just like every other composite we've specified and pass it to .load. Mine involves multiple recipes or multiple resolutions, so I get that warning about there being different resolutions. I'm going to do the native resampler, and when I do that, I now have my data array with the bands dimension and everything else set. I can now skip through that process of specifying how to stretch things, and I can do get enhanced image to look into that enhancement configuration, do the stretching the way I specified, doing that linear transformation, and I get the image that I had before. So what we've done is we've gone from using built-in recipes defined by somebody else to coming up with our own recipes, playing with the limits, seeing the changes interactively, and then storing those in a configuration file so that we could reuse them later. In the next lesson, we will reuse them again. Are there any questions with composites before I move on? No. Okay, I'm going to close. Yeah.
How does it know where to find the composite file?
By default, so how does it know where to find the composite file? So by default, it will look in, it will take everything that's built into SatPy, and then it will update that set of configuration with whatever a specific setting in SatPy. You can, there's an extra setting that I didn't say in here to specify where your configurations are. Maybe you have a certain directory on your system where you like to store configurations, so you could point it to there. And then it will also look in your current directory looking for a composites directory that has YAML files in it. Because our data is ABI, because the scene that we created was for ABI sensor, ABI instrument, it knew to look for the ABI.YAML file. There's also like this little thing at the top. It says sensor name visir is what that's supposed to say, visir/AB. This is telling SatPy that we are on an ABI, or we're using an ABI instrument, so here's all the composites for the ABI instrument. But ABI is also a vis-IR instrument. It's got visible channels, it has IR channels, so also load all of the composites for vis-IR instruments, any generic composite that can apply here. And those are also built in to SatPy. Okay. All right, I'm going to close these lessons. I'm going to close the YAML files. I'm going to go back to the notebooks directory. I'm going to shut down my notebooks that I had open. I'm going to load lesson 6, animations. So far we've been dealing with single time steps. We have GOES data, and I've been mentioning all this stuff about temporal resolution, and oh, it takes images all the time, rapidly, but we haven't actually used them. Now let's use them. We want to see things evolve over time. That is the main benefit of doing stuff like this. As part of the data you downloaded, you have mesoscale data, so that's that 1 minute resolution data. We're going to look at an hour's worth of that. And so if we run this first cell, we're using glob, and we're saying, give us all the files that have this date time in them. And when we list the file names, there's 960 files. If you wanted to create a scene for every one of these files, so there's 16 files per time step, because there's 1 file per channel. That's just how ABI is structured. If you wanted to create a scene for each one of these, you'd have to find a pattern in the file names to sort through them and do replacing and make sure that you organize them all correctly. SatPy comes with some utilities to do that for you. The way you access that is through the multi-scene object. The multi-scene can be treated very similar to a scene object. It just operates on multiple of them. So we're going to import the multi-scene, and we're going to use this class method called fromFiles. And we say, here are all of our file names. Here's the reader that I know knows how to read these files. Sort them and give me a multi-scene object. So if we run this, it takes a couple seconds, and we get a multi-scene object back. The multi-scene is I think in the documentation I still have it marked as experimental because it doesn't do everything I want it to do. But it operates similar to how Dask does things lazily. So it didn't actually, it might not create each one of those scenes right away. It will create them as it needs to process them. This saves you on processing time and memory usage and number of open files that it has to have. But it gives you an interface very similar to the scene. So we have a load method, so we can load the myRGB that you created in the last lesson. So we do that. We can resample, which will return a new multi-scene. So we'll do native resampling again. And I should have ran this before I started talking, because this will take a while. So run that last save animation cell. So save animation is a new function that's only available on the multi-scene, and what this is doing is using a library called image.io underneath, and underneath that it's using the FFmpeg tool, and it's generating the images for you, sending them to FFmpeg, and creating an MPEG-4 video. Through these keyword arguments, we said we want 12 frames per second. We gave it a file name. We did all the time formatting. And then what's happening underneath is the multi-scene is stepping through each scene that it created. So it grouped those files. It said, okay, these 16 files go with this time step. Let's load that channel. Let's do the native resampling. And now let's generate an image and write it to an MPEG-4 video. Hopefully this doesn't take too much longer. And so this is stepping through. What else is this doing? Yeah, and it's trying to load things as it needs them. Oh, it finished. So mine on my computer took 1 minute, 5 seconds. We loaded that RGB, so it's looking at those recipes again. If I navigate to my notebooks directory in my file browser, you should see a myrgb.mp4 file. So I can open that in QuickTime, for me at least. And so I now have an animation that I made with my RGB over time. And down by the player here, let's see if I can make this bigger. Can I make this a loop? Oh, loop. There we go. And so when the controls go away, the fire is right underneath those controls, and so we can see as the smoke increases, and we can analyze this, looking at the different colors, seeing how things evolve, using pre-configured RGB recipes and 5 lines of code or something like that. So the other option we could have gone with here is the multi-scene has a save datasets method. We could have saved all of these images to disk and done our own complex FFmpeg set of operations. FFmpeg or image.io also supports other types of animation formats like GIF or GIF, however you want to say that. Keep in mind those are much larger, and we're writing raw data arrays. FFmpeg is compressing things for us and making things a size that is reasonable. If we were to use PIL, which is what image.io would use, you're writing the raw data array, so you're ending up with an animated image, a GIF, that is very large, and GIF doesn't really compress well. So you end up with very large images. It's just better to use MPEG, please.
Can't you set the compression on FFmpeg through keywords or anything like that?
Yes, yeah, and so image.io allows extra keyword arguments, so you can control more of the frames per second and all of the encoding settings. It has some fairly logical defaults that are supposed to let it work on most machines. The one thing I've run into is that it's too high quality for PowerPoint, and so PowerPoint doesn't do well with large video files, and so I've had to use FFmpeg after the fact to lower the quality of the video. But otherwise, it works everywhere that I've seen. Yeah, so that's making an animation with the multi-scene. The next step in this, so let's save that. I'm going to run all of these cells, and I suggest you do the same, and then I'll talk about what they're doing. Okay, so if we start up at the top of this stacking, we are now loading VIIRS data. So I talked about how VIIRS data is orbiting around the poles, and so over time you end up with one orbit, and then the satellite goes around again, and you end up with another orbit. To make a full image of what you're looking at, or the area that you're looking at, you might need to, or you might want to, stack those orbits on top of each other. And that is what we're trying to do here. So we're taking the fire data, and I actually am loading, if you looked at the file names, there's JPSS1, so that's NOAA-20, and then there's MPP files, and I've loaded both of them. Okay, so now mine finished. But I'm creating a multi-scene the same way I did before, using from files, loading IO3, I'm resampling to a custom area that I defined, LCC projection, doing all this with the multi-scene, and then I'm using a new blend method, which by default will take every frame and stack the next frame on top of it. So it took one orbit, stacked the next one on top of it, and then when we plot this, it took about 40 seconds, I guess. This is actually two separate orbits from two different instruments that we've put on top of each other. If you had the time and I didn't make you download gigabytes of data, you would be getting a much larger image with much more data on it, and you can end up building an entire scene of just VIIRS polar orbiter data. Okay, so that's that. I wanted to do some examples of other type of videos you could do and why this is very neat. For animations, you have things like this, where you can get, this is Hurricane Florence. I don't remember what year that is from, I think 2018. Yeah, it has to be. And so you can actually see the rotation of the hurricane. I'm not sure how well that shows up on there. That was generated with SatPy, and I think I forgot to load the other one that I wanted. This is not out of the box with SatPy, but I wanted to show what's possible, is that this is VIIRS data. We're making what's called a true color RGB in the daytime, and then we use a special compositor to say, oh, at night I want a different image. So I have it loading that day-night band, and then I throw this into the multi-scene to give me one granule at a time. So this is as the satellite is orbiting, we're getting different sets of the swath and making this video as we go through time. Still working on making that make sense in a SatPy interface. Yeah, so that kind of thing is possible. I didn't mention there are a lot of different compositors in SatPy 2 that you might want to play with. So that's compositing and doing the multi-scene to use those composites. You could do the same thing with the stacking and the videos of using regular bands. I don't have any exercises for this because these steps take quite a while to process all of these frames. I'm sorry. So let's go on to the next lesson. Gonna go Cartopy GeoViews. So based on the survey, the idea I got is that most people in the room don't really use Cartopy, and I think very few use GeoViews. And that kind of works to my advantage here because I am not an expert on either of them, but we added some utilities to SatPy so that you can more easily communicate and use these tools. They have their advantages. They're very useful. I just don't have to use them all the time in my day-to-day job. But we'll see what they can do here. We're going to use ABI CONUS data again. We're going to use Cartopy to start out. We're going to create this scene. You could load whatever channel you want to load again. I'm going to stick with channel 7. And then we're going to have this big long Matplotlib box. And we'll run this and then we'll talk about it. So you should get an output image like this. I have my channel 7 data. I have the color bar still. I have lat long lines that are kind of far apart. And I have coastlines added. If we look at the code that generated this, I guess I should say what Cartopy is. Cartopy is kind of an extension of Matplotlib where it understands geographic information, so coordinate systems. It understands that there could be coastlines or other features on the Earth that you want to plot. To do that, it uses its own internal CRS object, coordinate reference system, and to use SatPy's loaded data with Cartopy, we have to convert our area definitions to Cartopy CRS objects. The way we do that is through this line of code. So this is taking our data array, getting the area, and then running this to Cartopy CRS method. That gives us a CRS object. We can then use fairly similar Matplotlib functions, so we create a figure. Now we're going to create an explicit axes object where we tell it the projection of this axis, the coordinate system for this is this projection. So we're saying we have a geostationary projection. use that for our figure axes. We get our data array. Because we're doing everything in Matplotlib, we can use the same utilities from Xray. So mydata.plot.imshow, and we tell it this data is in this coordinate system. So we give it that CRS again. We use coastlines and we use grid lines from the axis object to add those to the figure. So there is a lot of extra functionality in SatPy for adding other features. They have a whole gallery of examples of what you might want to do. This is a proof of concept, I guess. The other cell that's in this section shows how you can let SatPy do the resampling if you want. So here we're telling it we want a big, large plot array projection of all of our data. So it took that and it resampled it however it wanted to do it to get our data on the map. And so that's what we get as an output. It was all the same code except for I changed what CRS object I was using. And I took that from SatPy. So that's that. So that's really all I have for SatPy. In the links here, I have a SatPy tutorial by Phil Elson. He is one of the creators of SatPy. I highly recommend you read through that. It has some good advice and some extra examples. Their documentation, which I also have linked here, has a lot of, like I mentioned, a gallery of examples, which would be good to look at. GeoViews is a similar tool, providing interactive plots in notebooks and other interfaces to plot your data, interact with it. We're going to step through some examples of doing that. There are utility methods from SatPy to help us work with GeoViews, and we'll see some cool examples here. First, we have to import everything that GeoViews is going to use. This is pretty much copied and pasted from some of their examples. I just changed some of the defaults for the options I was setting. And then we take our scene that we have my channels, and we create this GeoViews object that GeoViews can then use to create plots. To GeoViews, we tell it we want to look at my channel, we tell it what color map we want, we tell it to add coastlines and borders. GeoViews handles that by you multiply, you use the star, the asterisk, on your GeoViews object. And if we run this, we get a nice warning, but then eventually we will get a plot, hopefully. Really? There we go. So this is still something I'm playing with on getting it to look better. I think what SatPy is doing here is it's hitting the edge of the data and trying to stretch it to fill the projection that it's using. By default, GeoViews is guessing what projection would be best to look at our data in. We're giving it the lat-lon values, or maybe it's giving it the CRS object. But we have a color map, and similar to Matplotlib's tools, we have tools on the side here. So we have this magnifying glass so we can zoom into certain areas. We have, I believe this is zooming with your mouse if you wanted to do that. So we can do that by clicking that button. And then there's also pan and zoom, or sorry, pan. So we can click the 4 arrows and move around. So it provides a similar interface to Matplotlib, but a different one. Plotting the data, we can hit this little refresh looking button to reset the axes. GeoViews also uses the CRS objects from SatPy, or it can use them. So we can run the same examples, but resample to a different area. So this next cell, this will resample in the same projection. So we provided, we told GeoViews here, projection equals CRS. And now we get that ABI scene that we've been looking at all day, but have the coastlines added. We have our color bar. Same kind of interface. We can, just like SatPy, have it do the resampling and have it do a Lambert conformal here. So this is also using those CRS objects from SatPy. Give it a sec. Same kind of idea where it's stretching the data. I'm working on that. But different projections, different views, different distortions, looking at the data interactively in Notebook. They have a lot more functionality than just plotting this. This next section shows some of that, and this is something one of our users came and said, I would like to look at my data in GeoViews. What do I need to do? And I said, I don't know. And they said, okay, I'll figure it out. And so they came up with this interface that takes advantage of GeoView's ability to give you sliders or tools on your plots. So if we run through these cells, we're going to start by loading the meso data again, create a new scene, but we're going to create a multi-scene. So this is the meso data that we made that video from. We're going to load channel 7. We're going to use that blend method, which previously we used to stack VIIRS orbits on, but we're going to give it the special time series and say, join these data arrays together on some time dimension. And if we do that, that will return a regular scene object, but where our 2D data is now 3D with a time dimension. So we took those mesoscale 1-minute time steps, blended them together into one data array, and then we can use the 2 GeoViews that we've used before, but telling it that we want to dynamically go through this data. So you should, if you run through these cells, have a slider on the right side. It's labeled time. And if you move this around, you will see the data as we step through it. So I'm going to use the zoom box to zoom in on the fire down here. And so now I can slide through here and look through all the data that I've loaded at least. You can go back and forth and do all your normal interactive stuff. And we've looked through color maps and added borders and coastlines. I believe this image is too zoomed in to get any actual coastlines. Yeah. So if I zoom out, you can see that there are coastlines there. And I went through this kind of fast, but are there any questions? And I know there weren't any exercises, but like I said, I'm not an expert. If anybody can give me hints or tips on how to do this better, I'm all ears. But I've shown you the basics of these tools and what they provide you. Any questions on that? Yes?
Do you have recommendations for dealing with data that need to wrap around the dateline?
Do you just want to view the data, or are you doing something with it?
So some of this comes from some open issues on Cartify, things like even just drawing grid lines is apparently onerous. But I've had some instances where I need to plot data that, say, appeared around New Zealand, do across the date lines and start doing interesting things.
It is one of the best problems of this, dealing with this data. I typically resample if I can, so that the dateline is not, or the anti-meridian I should say, is not the splitting point of my projection. So you could use Mercator and tell it, well, 0 isn't my starting point, 0 longitude, 180 is, or something like that. That is one way that I think dynamic area definitions can do that actually too. But yeah, I don't have a better suggestion than that. Not that I can think of offhand at least. All right. Okay, so this was an introduction to these tools. And this really kind of marks the last bit of the code part of this tutorial. We're getting towards the end. The last thing I have is talking about contributing to SatPy. So what we did today is we used SatPy and its scene object, mostly its scene object, to load data. I pointed out that there are multiple readers for SatPy. We used 2 of the semi-easier ones. We loaded data that I had you download. I got that data from, if you Google GOES-16 ABI, I believe I got it from Google's cloud computing. So NOAA has put their data up there on Google Cloud. They also have it on Amazon Web Services. So I downloaded the data from there. There are other services that provide that data. VIIRS data I got from NOAA Class. Every organization for these different satellites have their own websites or different tools for being able to download data. Like I mentioned, we were loading NetCDF and HDF5 files. There are many different instruments that have binary formats. Some use JPEG 2000 and some custom binary ones. Some use HDF4, depending on how old they are. Sometimes new ones use HDF4. Don't ask me why. But we can load that data into using a simple interface with the scene, ask for data sets that SatPy has configured for us, and get it into an Xray data array object. Once we have that, we can use any Xray tool that understands our data, which should be everything. One thing that is being worked on in the open source community with Xray is I'm trying to start a GeoXray project. There's also the RIO Xray project that is trying to kind of standardize how Xray data array objects record or specify this geolocation information. If that's something that's very important to you in your work, I can provide you some links to that. I'm hoping that it becomes semi-standard, and I'm trying to standardize it in SatPy, and other people are doing it in their own tools, and we're trying to make it the same across all these tools. So we loaded data with our scene. We wrote data to GeoTips NetCDF files. We plotted data with Xray's utilities and the standard Matplotlib tools. We loaded pre-configured composites, RGBs. We created our own composites, our own RGBs, our own channels, our own enhancements. We used those to make videos, MPEG videos, showing how the satellite data evolved over time. We did stacking of multiple orbits for polar data using resampling, a couple commands to get all of that data into one image. And we showed a quick view of what CartoPy and GeoViews can do and how you can provide SatPy's data to those tools. If there is a huge use case that you think SatPy is missing, you think something isn't working the way you would expect it, that's where I would ask you to let us know. SatPy has its own GitHub repository. I mentioned the PyTroll Slack. You can come talk to us, complain to us if you want. You can, doesn't have to be about SatPy or PyResample or any of our other libraries. You can just come talk about satellite processing and satellite instruments. But if you do have some issue, please raise an issue on GitHub, on the SatPy repository. Pull requests are always welcome. Let us know what you're using SatPy for, what you think could be done with it, what features you request. It would be great to add you onto the community. As far as what PyTroll and SatPy are using underneath, a lot of the tools we use today are listed in this, are shown in this graphic. We used Xray data array objects. They had Dask underneath. We used the basics of Dask, doing things like multi-threading, computing things when there was memory available. So we only computed a chunk of the data at a time, trying to save our systems from killing themselves. The Pangeo, this is the Pangeo logo. Pangeo is an open source community who strives to bring scientists to the compute, to the data. They're big supporters of having scientists go to cloud computing resources. I believe they have a couple talks this week. They want you to go on those cloud resources, get the people providing the data to put their data on those cloud services, so that you can work with them without having to have huge compute on your laptop and without having to download a ton of data like you did today. We use GeoViews, CartoPy, Matplotlib, use Matplotlib for almost everything. NumPy is underneath all of that. This tutorial is also, it's possible to load it with Jupyter Hub and Binder Hub and run this stuff on the cloud with Google. There's still a few bugs that I'm tweaking. All of the data was provided by NOAA. NOAA GOES-16 data is what we looked at, and the NOAA JPSS-1 or NOAA-20 and SUMI MPP VIIRS instrument. I hope that you got something out of this tutorial, even if you don't think you're going to use SatPy. Hopefully you learned a little bit about projections, even if you didn't want to, or satellite instruments in general. Thank you for coming. I hope you have a good week. Thank you.